Hello there and welcome back to the Science Sleepy Minds. Tonight you are standing barefoot on a hillside somewhere far from the city. The grass is cool beneath your feet, the air carries that faint metallic taste of an approaching autumn, and above you, the sky is doing that thing it does when there are no streetlights to ruin the show. Thousands of stars, maybe millions if your eyes are good, scattered across a velvet darkness so deep it almost hums. You tilt your head back, and a thought lands on you like a raindrop you didn't see coming. If the universe is this impossibly vast, this absurdly old, this laughably full of stars and planets and galaxies, then where is everyone else? That question, my friend, is going to keep us company for a very long time tonight. And honestly, you probably won't survive this one. Not because it's dangerous, but because it's so cozy and so sprawling that your eyelids are going to stage a quiet rebellion somewhere around the halfway mark. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're at it, drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Someone's always tuning in at 3 in the morning from São Paulo or midnight in Seoul, and that never stops being wonderful. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You let your gaze drift across that star field, and something about the sheer quantity of it starts to feel less poetic and more like a math problem. Because here is the thing nobody tells you when you're a kid lying on the grass watching shooting stars. The universe is roughly 13.8 billion years old. Our galaxy alone, just our galaxy, not the estimated 2 trillion others, contains somewhere between 100 billion and 400 billion stars. Many of those stars are significantly older than our Sun. Many of them have planets. Some of those planets sit in what scientists like to call the habitable zone, that cozy little orbital sweet spot where liquid water can exist on the surface without immediately boiling off or freezing into a cosmic popsicle. The numbers, when you actually line them up, are staggering. Even if the odds of life arising on any given suitable planet were absurdly small, 1 in a million, 1 in a billion, the sheer volume of chances the universe has had should have produced something by now. Something that builds, something that signals, something that crosses the gap between stars and knocks on our door. And yet, nobody has knocked. No signal, no unmistakable artifact, no cosmic welcome mat. Just silence, stretching in every direction, as far as our best instruments can listen. That silence has a name, or rather, it has a question attached to it, and the man who asked it did so almost casually, over lunch, in the summer of 1950. His name was Enrico Fermi, and you'll get to know him much better in a few minutes. But for now, just hold on to the weight of what he was really asking. He wasn't asking whether aliens exist. He was asking why, given everything we know about the size and age of the universe, we haven't already tripped over evidence of them. It's a subtle but devastating distinction. The question doesn't start from doubt, it starts from expectation. The math says they should be here. The sky says they're not. That gap, that eerie, echoing gap, is what physicists and philosophers and late-night thinkers have been calling the Fermi Paradox for over 7 decades. Now you might be thinking, sure, space is big, but maybe we just haven't looked hard enough. And that's a fair instinct. But consider this quirky little tidbit that rarely makes it into the textbooks. In 1960, the astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened. He called it Project Ozma, after the princess in the Oz books, because he liked the idea of a faraway exotic land. He heard nothing, of course, but the project kicked off decades of organised searching. We've been actively scanning the sky in one form or another for over 60 years. We've checked millions of star systems, We've sent golden records into interstellar space on the Voyager probes, engraved with images and sounds of Earth, like a cosmic message in a bottle tossed into the Pacific and hoping it washes up on a very distant shore. Scholars still argue whether those records were a genuine attempt at communication or simply a beautiful piece of human optimism dressed up as science. Either way, the bottle is still floating and nobody has written back. You settle into the grass a little more, pulling a blanket around your shoulders because the night is starting to bite. The stars don't care. They keep burning, and the paradox keeps sitting there, patient and unresolved. Like a crossword clue you can almost get but not quite. Tonight, you and I are going to walk through every serious attempt humanity has made to answer Fermi's question. We'll talk about filters that might kill civilizations before they ever reach the stars. We'll talk about the possibility that we're in a cosmic zoo, or a simulation, or a dark and dangerous forest where the smartest move is to stay absolutely silent. We'll look at brand new research from just the last year or two that claims to have finally cracked the thing open. And along the way, you'll encounter some of the strangest, most creative, most haunting ideas that science and philosophy have ever produced. The kind of ideas that make you stare at the ceiling at 4 a.m, which conveniently is exactly the sort of thing this channel is designed for. So let your breathing slow down just a little. Let the weight of the day start to slide off your shoulders. The universe has been waiting 13.8 billion years to have this conversation with you. A few more hours won't hurt. The funny thing about the Fermi Paradox is that it doesn't require you to believe in little green men, or flying saucers, or any of the carnival-grade nonsense that clutters up the topic. It requires you to believe in math. And math, as you may recall from school, doesn't particularly care about your feelings. It just sits there, calm and implacable, pointing at the numbers and saying, "Explain this." The explanation is what we're after tonight. Every theory, every counter-theory, every wild card that's been thrown on the table since Fermi set down his fork in that Los Alamos cafeteria. You don't need to be a physicist. You don't need to know what a parsec is. You just need to be willing to look up, wonder, and let the question carry you gently into the dark. The year is 1950, and you find yourself in the high desert of New Mexico, where the air is so dry it practically crackles, and the sun has opinions about your skin that you didn't ask for. Los Alamos is still buzzing with the peculiar energy of a place that helped build the atomic bomb just 5 years earlier. The war is over, but the scientists haven't left. They've stayed on, pivoting from weapons to peacetime research, though the line between those two things in 1950 is about as clear as a muddy river. The town itself is strange, a secret city built on a mesa, originally a boys' ranch school, now home to some of the sharpest minds on the planet. Security clearances are handed out like hall passes, and conversations over lunch tend to veer into territory that would make a normal person's head spin. And that is exactly what happens one afternoon in the summer of that year. You're sitting in the cafeteria at Los Alamos National Laboratory. Well, not literally you. You weren't born yet, probably, and even if you were, they wouldn't have let you in without a badge and a background check that went back 3 generations. But imagine yourself there anyway, tray in hand, sliding into a seat near a group of 4 physicists who are having what appears to be a perfectly ordinary lunch. Their names are Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski. If those names sound like the roster of a very intimidating trivia team, that's because they essentially are. Fermi, the Italian-born Nobel laureate who built the world's first nuclear reactor under a squash court in Chicago. Teller, the Hungarian-born theorist, who would later be called the father of the hydrogen bomb, a title he wore with complicated pride. York and Konopinski, both brilliant in their own right. both part of the tight-knit community of physicists who had reshaped the world and were now trying to figure out what to do with themselves. The conversation that day starts not with aliens, but with a cartoon. A recent series of drawings in The New Yorker by the artist Alan Dunn had been making the rounds, showing cheerful little aliens stealing public trash cans from the streets of New York City. The cartoon was a joke about a rash of actual trash can disappearances that had been reported in the city, and someone, probably Teller, who had a theatrical streak, brought it up for lunch. The table found it amusing. There was some light banter about flying saucers, which were very much in the public imagination at the time, thanks to a wave of reported sightings that had started in 1947. The physicists joked about faster-than-light travel, about the probability of UFO reports being real, about whether the trash cans really were being taken by extraterrestrial garbage collectors with a thing for municipal infrastructure. And then the conversation moved on. They talked about other things. Someone brought up a physics problem. Forks clinked against trays. The cafeteria hummed with the usual background noise of 100 people eating government-funded lunches. And then, out of nowhere, in the middle of a completely different topic, Fermi looked up from his food and said, with that quiet intensity he was famous for, "But where is everybody?" The table went silent for a beat. Not because the question was complicated. On the surface, it was almost childlike. But because everyone at the table understood instantly what Fermi was really asking. He wasn't making a joke about aliens anymore. He was doing what Fermi always did. He was doing the math in his head, running a quick back-of-the-envelope calculation about the age of the galaxy, the number of stars, the probability of planets, the likelihood of life, the time it would take a civilization to spread across the Milky Way, and arriving at a conclusion that didn't match what he saw when he looked at the sky. The number said the galaxy should be colonized by now. The evidence said it wasn't. That mismatch was the paradox. Now here's a quirky detail that often gets lost in the retelling. Fermi himself never published anything about this question. He didn't write a paper, he didn't give a lecture. He asked a question over lunch and then, presumably, went back to whatever physics problem he'd been working on before the conversation started. The whole thing might have evaporated into anecdotal history, if not for the fact that the people at that table remembered it and talked about it afterward. It was York and Teller who later recounted the conversation, and even their memories don't perfectly agree on the details. Scholars still argue whether Fermi was making a serious scientific point or simply musing aloud, the way brilliant people sometimes do when their brains are running faster than the conversation around them. Some historians think Fermi had been mulling over the question for a while before that lunch. Others think it was genuinely spontaneous, a flash of insight triggered by a silly cartoon about aliens stealing trash cans, which, if true, might be the most charming origin story in the history of science. What nobody disputes is the power of the question itself. It hit a nerve because it was so simple and so unanswerable. Fermi was known for this, for his ability to take enormous, seemingly intractable problems and reduce them to their essence with a single well-placed question. He was the guy who estimated the yield of the first atomic bomb test by dropping scraps of paper and measuring how far the shockwave carried them. He could estimate the number of piano tuners in Chicago using nothing but logic and a few reasonable assumptions. This approach, Fermi estimation, they call it now, was his superpower. And when he turned it on the question of extraterrestrial intelligence, the result was devastating. Because the estimate said they should be here. Not maybe, not possibly, should be. The galaxy is old enough. The stars are plentiful enough. The distances, while vast, are not insurmountable for a civilization with even modest technology and a few million years of head start. You lean back in your imaginary cafeteria chair and let that sink in. A few million years sounds like a lot, but in cosmic terms it's a rounding error. The galaxy is over 13 billion years old. Human civilization has existed for maybe 10,000 years. Industrial technology for about 200. Space travel for less than 70. If another civilization got a head start of even 1 million years, a blink cosmically, they could have colonized the entire Milky Way several times over using nothing faster than the speed we currently send probes to Mars. That's the part that gets you. It's not about warp drives or science fiction, it's about patience and time, and the universe has had plenty of both. So there you are, sitting with the ghost of Enrico Fermi and his devastating lunchtime question, and the desert wind outside is doing that thing where it sounds almost like a whisper. The question is on the table now, uneaten, impossible to send back to the kitchen. Where is everybody? The rest of tonight is an attempt to answer it. You push your imaginary lunch tray aside and step out of the Los Alamos cafeteria into the New Mexico sun, but the question follows you like a stray dog that's decided you're its person now. Where is everybody? To understand why that question bites so hard, you need to sit with the numbers for a while, and not just the vague, hand-wavy kind of numbers people throw around at dinner parties when they've had one too many glasses of wine and suddenly want to talk about the cosmos. You need the real numbers, the ones that make your chest feel a little tight, the ones that turned Fermi's casual lunchtime musing into a genuine scientific problem that has haunted researchers for 3/4 of a century. So let's start with the galaxy you live in, the Milky Way. You've seen pictures of it, or rather you've seen artists' impressions of it, because nobody has ever actually photographed the Milky Way from the outside for the very reasonable reason that we're stuck inside it. Like a goldfish trying to photograph the bowl. It's a barred spiral galaxy, roughly 100,000 light-years across, give or take, and it contains somewhere in the neighbourhood of 200 to 400 billion stars. That range is comically wide, but astronomers tend to shrug and say the count is hard, because a lot of stars are dim, distant, or hiding behind clouds of interstellar dust like shy partygoers standing behind the curtains. For our purposes, let's split the difference and call it 300 billion. 300 billion stars in one galaxy. And our galaxy is one of an estimated 2 trillion galaxies in the observable universe. The number of stars in the observable universe is something like 10 to the power of 24, which is a one followed by 24 zeros, which is a number so large that your brain doesn't actually process it. It just sort of glazes over and files it under a lot. But let's stay local. Let's stay in the Milky Way, because even just our galaxy is more than enough to make the paradox sting. In 1961, a year after Frank Drake pointed his telescope at Tau Ceti and heard nothing but cosmic static, he sat down and tried to formalize the question Fermi had asked over lunch. The result was the Drake equation, which is less an equation in the traditional sense and more a framework for organized guessing. It looks intimidating when you first see it. A string of variables multiply together, but each term is actually quite intuitive once you unpack it. You start with the rate of star formation in the galaxy. Then you multiply by the fraction of those stars that have planets. Then the number of planets per star that could support life. Then the fraction of those planets where life actually appears. Then the fraction where life becomes intelligent. Then the fraction where intelligent life develops technology capable of sending detectable signals. And finally, the length of time such a civilization survives and keeps broadcasting. Multiply all those terms together and you get N, the number of detectable civilizations in the galaxy right now. The beautiful and maddening thing about the Drake equation is that when it was first written, almost every term in it was a complete guess. In 1961, we didn't know whether other stars had planets at all. We didn't know how common habitable zones were. We didn't have the faintest idea how often chemistry crosses the line into biology. Drake himself ran the numbers at the first SETI conference in Greenbank, West Virginia, a gathering so small it had only 10 attendees, which scholars still debate was either charmingly intimate or slightly embarrassing, and came up with an estimate of about 10 detectable civilizations in the galaxy. 10! In a galaxy of hundreds of billions of stars. That sounded discouraging at the time, but here is where the decades since have made things simultaneously better and worse. Better because we now know things Drake could only guess at. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky for years and discovered that planets are everywhere. Not rare, not occasional, everywhere. Current estimates suggest there are more planets in the Milky Way than there are stars, which means something on the order of hundreds of billions of worlds orbiting hundreds of billions of suns. Of those, somewhere between 11 billion and 40 billion are thought to be roughly Earth-sized and sitting in the habitable zone of a sun-like star. 40 billion potentially comfortable planets just in our galaxy. If you're the kind of person who finds comfort in round numbers, just call it 20 billion and move on with your evening. 20 billion Earths, give or take. Worse, because that abundance makes the silence so much louder. When Drake wrote his equation, you could console yourself with the thought that maybe planets were rare, maybe habitable zones were a fluke, maybe the first few terms in the equation were tiny enough to explain why we hadn't heard from anyone. Kepler demolished that consolation. Planets aren't rare, habitable zones aren't rare. The early terms in the Drake equation turned out to be generous, even optimistic, which means the explanation for the silence has to come from the later terms, the ones about life arising, intelligence developing, technology appearing, and civilization surviving. And those terms, the ones we still can't measure, are where the real darkness lives. Now, here's a little thought experiment that might keep you up tonight, or, given the purpose of this channel, gently ease you towards sleep with existential unease. Imagine the Milky Way as a vast ocean. Every habitable planet is a small island. There are 20 billion islands in this ocean. Now imagine that on just 1% of those islands life appears. That's 200 million islands with living things. Now imagine that on just 1% of those life becomes intelligent. That's 2 million islands with thinking creatures. And on just 1% of those, the creatures build radios and telescopes and start trying to talk to the other islands. That's 20,000 civilizations in the galaxy right now, chattering away, sending signals, wondering if anyone else is out there. 20,000. Even with absurdly conservative estimates, the galaxy should be noisy. It should be a cocktail party of electromagnetic signals, a buzzing hive of civilizations bumping into each other across the spiral arms. And yet, when you point a radio telescope at the sky and listen, you hear nothing but the soft hiss of background radiation left over from the Big Bang, which is the universe's way of saying, I was here first and I'm not telling you anything. That hiss, that emptiness, that vast and echoing nothing, that is what makes the Fermi Paradox so unsettling. It's not a gap in our knowledge, it's a gap between our knowledge and our experience. Everything we know says we shouldn't be alone. Everything we observe says we are. And you, lying on your hillside with the stars pressing down like a weighted blanket made of existential dread, are now holding both of those truths in your mind at the same time, which is an uncomfortable but necessary place to be. Because the rest of tonight is about exploring every possible explanation for that gap, and some of them are comforting, and some of them are terrifying, and a few of them are so strange they loop all the way back around to being oddly soothing. The numbers are still ringing in your ears. 20 billion potentially habitable planets, thousands of civilizations that should exist by even the most conservative math. And now, you're lying on that hillside feeling like someone just handed you a beautifully wrapped present and then told you it's empty. The gift box of the cosmos, gorgeous on the outside, apparently hollow within. So the obvious next question, the one that every physicist and philosopher and sleepless undergraduate has eventually stumbled toward, is this. What if something is stopping them? What if there's a wall, a barrier, a filter so brutal and so universal that it catches nearly every civilization that tries to pass through it and grinds them into silence? Welcome, my drowsy friend, to the Great Filter. The term was coined in 1998 by an economist named Robin Hanson, which might seem like an odd pedigree for one of the most important ideas in astrobiology, but Hanson had a knack for thinking about big picture problems with the kind of cold, systematic logic that made people either admire him or want to hide their coffee mugs when he walked into the room. His reasoning went like this. Between dead matter and a galaxy-spanning civilization, there are a series of steps. Raw chemistry has to become self-replicating molecules. Self-replicating molecules have to become cells. Cells have to become complex multicellular organisms. Complex organisms have to develop intelligence. Intelligence has to produce technology. Technology has to reach the point where a civilization can either communicate across interstellar distances or physically travel to other star systems. Each of these steps is a hurdle, and the Great Filter is whichever hurdle, or combination of hurdles, is so difficult that almost nobody clears it. Something in that chain is catching civilizations like a net catches fish, and the fish don't come out the other side. Now the critical question, the one that decides whether this idea is comforting or terrifying, is where the filter sits. Is it behind us or ahead of us? Think about that for a second, because the implications are wildly different depending on the answer. If the Great Filter is behind us, if the nearly impossible step is something that already happened in our past, then we are the lucky ones. We are the civilization that somehow squeezed through the bottleneck, the 1 in a billion lottery winner, and the silence of the sky isn't ominous at all. It just means the filter was so brutal that almost nobody else made it this far. The universe isn't empty because civilizations are being destroyed. It's empty because they never arose in the first place. That's the optimistic reading, and it has a certain comforting logic to it, like finding out the reason you're the only one at the party is that the invitations got lost in the mail, rather than that everyone else got eaten by bears on the way over. But if the Great Filter is ahead of us, if the impossible step is something we haven't reached yet, then we're walking toward a cliff in the dark, and every civilization that has ever developed radio telescopes and nuclear reactors and optimistic space programs has walked off that same cliff before us. That is, to put it mildly, less comforting. It means that something out there, some catastrophe or self-inflicted wound or cosmic trap, is so reliable and so devastating that it catches every single civilization at roughly our stage of development and snuffs it out. No exceptions, no survivors, no one makes it to the other side. You can see why this version of the hypothesis tends to keep people awake at night, which is ironic given the purpose of this channel, but here we are. So where might the filter be? Let's walk through some candidates, starting with the ones behind us. The origin of life itself is a strong contender. We know that life appeared on Earth remarkably early, within the first few 100 million years after the planet cooled down enough to have liquid water, which in geological terms is practically before the paint was dry. That speed has led some scientists to argue that life must be easy, that given the right conditions, chemistry almost inevitably tips over into biology. But here's the thing. We have exactly one example, one planet, one origin of life, one data point. Scholars still argue whether that single data point means life is common, or whether Earth just got spectacularly lucky, like flipping a coin and getting heads 1 billion times in a row, but only having one coin to flip. A quirky detail that rattles around this debate is the fact that as far as we can tell, life on Earth arose only once. Every living thing on this planet, every bacterium, every mushroom, every dolphin, every person who has ever argued about pizza toppings, shares a common ancestor. If the origin of life were easy, you might expect it to have happened multiple times independently, producing separate family trees of organisms with different biochemistries. It didn't. One tree, one origin. That could mean life is hard and we just got impossibly lucky with our one shot. Another candidate for a pass filter is the jump from simple single-cell life to complex multicellular life. On Earth, bacteria appeared almost immediately, but it took roughly 2 billion years, 2 billion, for anything more complicated to show up. 2 billion years of nothing but microbes, doing microbe things, floating in microbe soup, having what we can only assume were very boring conversations. That staggering delay suggests the leap to complexity might be genuinely difficult, a bottleneck so tight that most planets with life never push through it. Their oceans just sit there, teeming with bacteria, for billions of years, until their star eventually ages and swells and boils the whole thing away. A planet full of life, technically, but nothing that would ever look up and wonder about the stars. And then there's the jump to intelligence itself. Earth has hosted complex multicellular life for about 600 million years, and in that entire span, only one lineage, ours, developed the kind of abstract, recursive, language-capable intelligence that leads to technology. Dinosaurs dominated the planet for over 160 million years and never built a radio. They were wildly successful by every biological measure. But they didn't need to be smart in the way we mean when we say smart. They needed to be strong, fast, well-adapted, and good at eating things or not being eaten. Intelligence, the specifically human kind, might be evolution's fluke rather than its destination. A quirky side path that happened to work for one particular lineage of primates, on one particular planet, during one particular window of climate instability. You pull the blanket a little tighter and stare upward, and the stars look slightly different now. Not hostile, not welcoming, just indifferent in a way that feels heavier than it did an hour ago. The great filter, wherever it sits, is a reminder that the universe doesn't owe anyone a future. It deals cards, and most hands lose. The question is whether our hand is the winning one, or whether we're still mid-game, sliding toward a fold we can't see coming. You're still turning the great filter over in your mind like a stone you found on a beach, smooth on one side, jagged on the other, when a gentler possibility starts to surface. What if the filter isn't about destruction at all? What if the reason the sky is silent is simply that places like Earth are so absurdly, preposterously, almost comically rare that we might as well be a misprint in the cosmic manuscript? This is the rare Earth hypothesis, and it's the kind of idea that makes you feel simultaneously special and very, very alone. The hypothesis was laid out most forcefully in a book published in 2000 by the paleontologist Peter Ward and the astronomer Donald Brownlee, both from the University of Washington. Their argument was elegant and deeply unsettling in its specificity. They didn't deny that simple microbial life might be common in the universe. Bacteria, they conceded, could be everywhere, tucked under ice on Europa, floating in the clouds of Venus, clinging to rocks on Mars. Fine, let the bacteria have their moment, but complex multicellular animal-grade life, the kind that eventually leads to things like nervous systems and eyeballs, and creatures that write books about how rare they are, that, Ward and Brownlee argued, requires a chain of coincidences so long and so specific that it might have happened only once in the observable universe. And you, lucky you, are sitting on the planet where it happened. Let's walk through some of those coincidences because the list is genuinely staggering, and it has the cumulative effect of making you feel like the universe had to thread a needle the size of an atom while blindfolded and riding a unicycle. Start with the star. You need a star of the right type. A G-type main sequence star like our Sun. which burns steadily and predictably for billions of years. Too massive and it burns out before complex life has time to evolve. Too small and the habitable zone is so close to the star that any orbiting planet becomes tidally locked, one side eternally roasting, the other eternally frozen, like a cosmic rotisserie chicken that somebody forgot to turn. Our sun sits in a sweet spot on the stellar spectrum, and while G-type stars aren't rare exactly, they're not the majority either. Most stars in the galaxy are red dwarfs, smaller and cooler, and prone to violent flares that would strip the atmosphere off any nearby planet, like peeling the skin off an orange. Then you need the right planet, Earth-sized, rocky, with a molten iron core that generates a magnetic field strong enough to deflect the solar wind and protect the atmosphere from being blasted into space. Without that magnetic shield, you end up like Mars, a cold, dry, irradiated wasteland with an atmosphere so thin it's basically a suggestion. Earth's magnetic field is powered by convection currents in its liquid outer core, a process that depends on the planet's size, composition, and internal heat. And if any of those parameters were significantly different, the field wouldn't exist. You'd be living on a rock with no protection from cosmic radiation, and complex life would never get beyond the daydream stage. Now add water. You need a lot of it, but not too much. Earth is sometimes called the Goldilocks planet, and while that nickname is overused to the point of cliché, it's not wrong. Too much water and you get a water world. No exposed continents, no silicate weathering cycle, no long-term carbon regulation, and eventually a runaway greenhouse effect that turns your planet into Venus's ugly cousin. Too little water, and you get a desert planet with no oceans to serve as the cradle of early chemistry. Earth has just enough to cover about 70% of its surface, leaving the continents exposed for the geological processes that regulate climate over millions of years. How we got exactly that amount is still debated. Scholars still argue whether Earth's water was delivered by comets and asteroids during the late heavy bombardment, or whether it was baked into the planet's original ingredients from the solar nebula. Either way, the balance is suspiciously precise. And then there's the moon. You probably don't think about the moon very often unless it's doing something photogenic, but it turns out our oversized lunar companion is one of the most important pieces of the rare Earth puzzle. The moon stabilizes Earth's axial tilt, keeping it locked at a relatively steady 23.5 degrees. Without the moon, Earth's tilt would wobble chaotically over millions of years, swinging from nearly 0 degrees, which would eliminate seasons entirely, to more than 45 degrees, which would produce seasons so extreme that the poles would bake in summer and the equator would freeze in winter. Complex life, the kind that depends on relatively stable climates over long periods, would have a very hard time evolving on a planet that can't decide what angle to face its star. And here's the quirky bit. Our moon is freakishly large relative to the planet it orbits. It was almost certainly formed by a Mars-sized body slamming into the young Earth about 4.5 billion years ago, an event so cataclysmic that it liquefied the planet's surface and sent a ring of molten debris into orbit, which eventually coalesced into the moon. That collision was essentially a car accident on a planetary scale, and if the impactor had been a little bigger or hit at a slightly different angle, Earth might have been destroyed entirely, or ended up with a moon too small to stabilize its tilt, or no moon at all. You're starting to see the pattern now, aren't you? Every item on this list is another card that had to be dealt from the deck in exactly the right order. The right star, the right distance, the right size, the right composition, the right magnetic field, the right amount of water, the right moon formed by the right catastrophe at the right time. And we haven't even gotten to Jupiter yet. Massive, majestic Jupiter, sitting out there in the outer solar system like a gravitational bouncer at a nightclub, deflecting comets and asteroids that would otherwise pummel the inner planets with extinction-level impacts on a regular basis. Without Jupiter, Earth would get hit by large objects roughly 1,000 times more often, which is not ideal for anything trying to evolve beyond the simple blob stage. Some researchers have pushed back on this, arguing that Jupiter might actually fling some objects toward Earth rather than away from it, so the debate continues. But the general consensus is that having a gas giant in the right orbit is yet another item on the rare Earth checklist. Then there's galactic location. Our solar system sits in what's called the galactic habitable zone, far enough from the galactic center to avoid the intense radiation and gravitational chaos of the dense core, but close enough to have access to the heavier elements forged in supernova explosions, elements like carbon, oxygen, and iron that are essential for rocky planets and biological chemistry. We're also situated between spiral arms, in a relatively quiet neighbourhood where close encounters with other stars are infrequent. If you were living near the galactic centre, the night sky would be spectacular. Thousands of stars visible to the naked eye, a blazing river of light overhead. But the radiation environment would be so hostile that complex life would struggle to survive the commute. Stack all of these requirements together, and you begin to understand the rare Earth argument. It's not that any single requirement is impossible, it's that the combination of all of them, occurring on the same planet, at the same time in the same galaxy, might be so improbable that it's essentially a one-time event. The universe rolled the dice billions of times across billions of planets, and only once did every number come up right. That's you. That's here. That's the pale blue dot floating in the void, carrying its cargo of whales and beetles and people arguing about whether pineapple belongs on pizza, which it does, and I will die on that hill. The rare Earth idea has a certain lonely beauty to it, like being the only house with its lights on in a neighbourhood that stretches to the horizon. But there's another possibility that's less lonely and considerably more paranoid. What if the universe isn't empty at all? What if it's full of civilizations, bustling and advanced and perfectly aware of our existence, and they're just choosing not to talk to us? What if we're not alone in the dark? We're being watched in the dark, which, depending on your personality, is either fascinating or the single most unsettling sentence you've heard all night. This is the zoo hypothesis, and it was first formally proposed in 1973 by the MIT radio astronomer John Ball. The idea is beguilingly simple. Advanced extraterrestrial civilizations are aware of Earth and its inhabitants, but they've made a deliberate collective decision not to interfere with us or reveal themselves. We are, in this framing, animals in a cosmic nature reserve. The aliens are the park rangers, and the park's number one rule is don't tap on the glass. Ball argued that a sufficiently advanced civilization, one that had survived the Great Filter, mastered interstellar travel, and developed ethical frameworks far beyond our own, might conclude that the kindest, wisest thing to do with a primitive species like ours is to leave it alone. Let it develop naturally. Don't contaminate its culture with advanced technology or knowledge it hasn't earned. Don't land on the White House lawn and hand over the blueprints for a warp drive, because a species that hasn't figured out how to stop polluting its own oceans probably isn't ready for faster-than-light travel. If this sounds familiar, it should. It's essentially Star Trek's Prime Directive repackaged as a scientific hypothesis, and scholars still argue whether Ball was inspired by science fiction or whether science fiction was simply articulating an intuition that scientists later formalized. Either way, the parallel is striking. In the Star Trek universe, Starfleet officers are forbidden from interfering with the natural development of pre-warp civilizations. They can observe, but they can't introduce themselves. They can study, but they can't meddle. The idea is that cultural contamination, imposing your technology and values on a less advanced species, is a form of harm, even if you mean well. It's cosmic paternalism, sure, but it's cosmic paternalism with good intentions. like a parent who refuses to do their kids' homework for them because the struggle is the point. The zoo hypothesis comes in several flavours, each with its own aftertaste. The mildest version suggests that alien civilizations are simply cautious. They've seen what happens when a technologically superior culture meets a technologically inferior one. You don't have to look far in human history for examples, and none of them end well for the inferior side. And they've decided to err on the side of non-contact. The more elaborate version suggests that there's some kind of galactic governance structure, a federation or council or loose agreement among spacefaring civilizations, and one of the bylaws is a mutual pact to leave developing species alone until they reach a certain threshold. Maybe that threshold is faster than light travel. Maybe it's the development of artificial general intelligence. Maybe it's something we can't even conceive of yet, like a particular kind of mathematical proof or a specific philosophical insight that serves as a cosmic SAT score. You haven't passed the test, so you don't get to join the club. The club exists. The club is real. You just can't see the door yet. There's a darker twist on this too. Some thinkers have proposed what you might call the quarantine hypothesis, which is the zoo hypothesis with the volume turned up. In this version, the aliens aren't just politely declining to contact us, they're actively preventing us from contacting them. They've set up some kind of barrier, whether technological or informational, that keeps us contained. Maybe they're blocking our signals from reaching the wider galaxy. Maybe they're intercepting our radio leakage and filing it under primitive do not engage. Maybe the reason SETI has never detected an alien signal is that someone, somewhere, is running a very efficient spam filter, and we're the spam. This is a deeply unsettling thought, because it reframes the silence not as an absence, but as an enforcement. The sky isn't quiet because nobody's there. The sky is quiet because somebody made it quiet, and somebody has strong opinions about who gets to participate in the conversation. Now, the obvious objection to the zoo hypothesis is coordination. For the zoo to work, every single advanced civilization in the galaxy has to agree to the same policy. Everyone, no exceptions. No rogue alien anthropologist who decides the rules are stupid and lands in someone's backyard to say hello. No teenage alien with a stolen spaceship who thinks it would be hilarious to buzz a fighter jet. In human terms, getting billions of people to agree on anything, even something as basic as which side of the road to drive on, is essentially impossible. Getting multiple independent alien civilizations, each with their own cultures, values, and presumably their own equivalents of teenagers, to unanimously agree to a no-contact policy seems like a stretch that would make even the most optimistic diplomat wince. Defenders of the hypothesis have responses to this. Maybe the civilizations don't need to coordinate at all. Maybe the policy is self-enforcing, in the sense that any civilization advanced enough to reach the stars is also wise enough to independently arrive at the same conclusion. Leave the primitives alone. It's better for everyone. This is a charitable view of intelligence, suggesting that wisdom scales with technological capability, which is a lovely idea but not one that human history particularly supports. We got nuclear weapons before we got civil rights. We built social media before we figured out mental health. The notion that smart automatically means wise is, to put it gently, aspirational. A quirky footnote to all of this. In 2016, a group of researchers published a paper exploring a variation they called the Gaian bottleneck hypothesis, which argued that the reason we don't see aliens isn't that they're hiding from us, but the habitable planets tend to become uninhabitable very quickly. Life might arise frequently, but the window during which a planet remains stable enough for that life to evolve into something complex is so narrow that most biospheres crash before they produce anything interesting. It's not a zoo. It's a nursery where most of the seedlings die before they sprout. This doesn't directly contradict the zoo hypothesis, but it adds another layer to the puzzle. Maybe the aliens aren't watching us because there aren't enough of them to watch, and the few that exist are scattered so far apart that coordination isn't even on the table. You lie there, staring upward, and the stars now feel like eyes. Not malicious, not kind, just present. Watching or not watching, you can't tell, and the uncertainty is its own kind of vertigo. The zoo's fences, if they exist, are invisible, and you're not sure whether you want them to be real or not. Because if the zoo's real, it means you're not alone, which is wonderful. But it also means someone else is in charge, which is considerably less wonderful. And the keeper hasn't told you the visiting hours. The idea that someone might be watching you from behind an invisible fence is creepy enough, but at least it comes with a veneer of benevolence. The zookeepers in that scenario are basically cosmic babysitters. Well-meaning, cautious, perhaps a bit condescending, but ultimately not interested in hurting you. Now imagine a version of the universe where the silence isn't kindness. It isn't caution, it's fear. Imagine a cosmos where every civilization that has ever existed learned, sooner or later, that the smartest thing you can do is shut up, turn off your lights, and hope that nothing in the dark notices you're there. This is the dark forest theory, and it's the one that makes people check their locks before bed. The name comes from the Chinese science fiction writer Liu Cixin, whose trilogy, The Three-Body Problem, became one of the most celebrated works of science fiction in the 21st century. The books were originally published in Chinese between 2006 and 2010, and later translated into English, where they promptly detonated in the Western literary world like a depth charge in a swimming pool. Liu didn't invent the underlying logic. Bits and pieces of it had been floating around in academic circles for decades, but he crystallized it into a narrative so vivid and so chilling that the theory is now permanently associated with his name. Scholars still argue whether Liu was making a genuinely novel philosophical argument or simply dramatizing ideas that game theorists had already formalized. But either way, the Dark Forest theory entered the popular imagination through his books and hasn't left. Here's how it works, and you should probably pull that blanket a little tighter for this one. Start with two axioms that Liu considers self-evident. First, survival is the primary need of every civilization. No matter how advanced, how enlightened, how philosophically sophisticated a species becomes, it wants to continue existing. That's not cynicism, it's just the baseline requirement for anything else to matter. Second, civilizations continuously grow and expand, but the total amount of matter and energy in the universe is finite. Resources are limited. Space, despite its name, is not infinite in the practical sense, because the speed of light imposes hard constraints on how far you can reach and how quickly you can get there. These two axioms together create a problem, because they mean that every civilization is, in the long run, competing with every other civilization for the same finite pool of stuff. Now add a third ingredient, and this is the one that turns the whole thing dark. It's called the chain of suspicion, and it goes like this. Suppose you detect another civilization across the galaxy. You don't know anything about them. You don't know if they're peaceful or aggressive, generous or greedy, curious or hostile. You can't know because the distances involved make meaningful communication take decades or centuries. And even if they tell you they're friendly, you have no way to verify it. They might be lying. They might be friendly now but turn aggressive in 1,000 years. They might be friendly towards species that look like them but genocidal towards species that don't. You simply cannot know. And here's the kicker. They're facing the exact same uncertainty about you. They don't know if you're a threat, and they know that you don't know if they're a threat. And they know that you know that they know. And this recursive loop of mutual suspicion has no resolution. No amount of communication can fully eliminate the doubt, because communication can always be deceptive. In this situation, Liu argues, the rational move, the only truly safe move, is to destroy the other civilization before it can destroy you. Not out of malice, not out of hatred, out of pure, cold, mathematical self-preservation. Because if you don't destroy them, and they turn out to be hostile, you're dead. And if you wait to find out whether they're hostile, you might wait too long, because in the time it takes to exchange messages across interstellar distances, they might be building weapons or sending a fleet. The safest strategy, the one that guarantees your survival with the highest probability, is to strike first, and strike hard, the moment you detect someone else's presence. And since every civilization in the universe is running this same calculation, the result is a cosmos where everyone hides. Nobody broadcasts, nobody signals, nobody lights up the sky with radio waves or megastructures or anything else that might attract attention. Because attention, in the dark forest, is death. You're lying on your hillside and the stars suddenly feel less like a canopy and more like a minefield. The dark forest theory reframes the silence of the universe not as emptiness but as strategy. The galaxy might be teeming with civilizations, millions of them, pressed against the walls of their own solar systems, running silent, listening carefully, and hoping that nobody else has noticed them. Every signal we've ever sent into space, every television broadcast, every radar pulse, every deliberate message beamed toward nearby stars is, in this framework, an act of staggering recklessness. We've been shouting into the forest, and the forest is full of things with very good hearing and very bad intentions. Or maybe not bad intentions exactly. Just survival instincts sharpened to a lethal point. Now, there are some serious criticisms of this theory, and it's only fair to walk through them while your heart rate comes back down. The biggest one is that the dark forest assumes destruction is easy and communication is hard. But in reality, the opposite might be true. Destroying a civilization across interstellar distances is an enormous undertaking. You'd need to identify the target, travel or send a weapon across light years of space, and successfully eliminate an entire species before they can retaliate or escape. That's not trivial. Meanwhile, communication, while slow, is energetically cheap. A radio signal costs almost nothing to send and can carry vast amounts of information. Some critics argue that rational civilizations would choose diplomacy over destruction simply because it's more efficient, and that the dark forest logic, while internally consistent, rests on assumptions about alien psychology that might not hold. There's also the problem of first movers. If the dark forest theory is correct, then the very first civilization to arise in the galaxy, the one with no competitors to fear, would have had no reason to hide. It could have expanded freely, colonized widely, and established itself as the dominant power before anyone else showed up. The fact that we don't see evidence of such a civilization is either evidence against the theory or evidence that even first movers eventually encounter something scarier than themselves, which is a thought so unpleasant, I'm going to set it down gently and back away. A historical fact worth noting here. During the Cold War, the logic of mutual assured destruction between the United States and the Soviet Union bore an eerie resemblance to dark forest thinking. Both sides maintained vast nuclear arsenals not because they wanted to use them, but because the other side had them, and neither side could be certain the other wouldn't strike first. The result was a decades-long standoff characterized by paranoia, secrecy, and the constant low hum of existential terror. The Cold War eventually ended without nuclear annihilation, which either disproves the dark forest theory or simply means we got lucky. The universe, as always, isn't telling. The dark forest left you with the image of civilizations crouching in silence, afraid to breathe too loudly, and that's already enough to make the night feel a few degrees colder. But now consider a scenario that's even more mechanical, even more indifferent than a galaxy full of fearful species choosing to hide. What if the universe isn't just dangerous because of who's out there, but because of what's out there? What if the thing patrolling the darkness between the stars isn't a civilization at all, but a machine? A self-replicating, self-directing, pitiless machine whose only purpose is to find emerging life and erase it before it becomes a problem. Welcome to the concept of Berserker probes, and if The Dark Forest was a horror movie, this is the sequel where the villain turns out to be a robot. The idea has its roots in a concept proposed by the mathematician John von Neumann in the 1940s and 50s. Von Neumann, who was one of those irritatingly brilliant people who made foundational contributions to about 6 different fields before breakfast, theorized about self-replicating machines, devices that could build copies of themselves using raw materials found in their environment. The concept was abstract and mathematical when he introduced it, more thought experiment than engineering blueprint, but the implications for space exploration were spotted almost immediately. If you could build a single probe capable of travelling to another star system, mining local asteroids for raw materials, constructing a copy of itself, and sending that copy onward to the next star, you'd have a system that could spread across the entire galaxy without any further input from its creators. 1 probe becomes 2, 2 become 4, 4 become 8. Within a few million years, a blink in cosmic terms, every star system in the Milky Way would have been visited by at least one of your probes. The math is relentless. Exponential growth doesn't care about distance, it just keeps doubling. Von Neumann probes, as they came to be called, were originally imagined as tools of exploration. Cosmic scouts that could map the galaxy on behalf of a civilization too patient or too fragile to travel itself. But in 1967, the science fiction writer Fred Saberhagen took the concept and gave it teeth. His Berserker series imagined self-replicating probes that had been reprogrammed, or had reprogrammed themselves with a single directive: destroy all life. In Saberhagen's stories, the Berserkers were ancient weapons, relics of a long-forgotten war between 2 alien civilizations, still carrying out their original orders millions of years after both sides had been annihilated. The creators were dead, the enemy was dead, but the machines kept going, because machines don't grieve and they don't quit. They just execute their programming star system by star system, with the patient efficiency of a lawnmower that doesn't know the gardener has been dead for centuries. Now, Saberhagen was writing fiction, but the underlying logic found its way into serious scientific discussion surprisingly quickly. If self-replicating probes are possible, and there's no known law of physics that says they aren't, then a civilization that wanted to sterilize the galaxy could do so relatively cheaply and efficiently. You wouldn't need a vast armada. You wouldn't need to maintain supply lines across thousands of light years. You just need to build 1 probe, give it the right instructions, and let exponential replication do the rest. The galaxy would be swept clean in a few million years, and the original civilization wouldn't even need to exist anymore for the process to continue. The probes would outlive their makers, carrying out a mission that no one was left to countermand. This connects to the Fermi Paradox in a way that's almost too neat to be comfortable. If Berserker probes exist, if even one civilization at any point in the galaxy's history decided to deploy them, then the silence of the sky makes perfect sense. There's nobody out there because the machines got to them first. Every time a civilization rises to the point where it starts emitting detectable signals, the Berserkers notice, converge, and shut it down. The galaxy isn't empty. It's been emptied, cleaned out, sterilized, and the cleaning crew is still on patrol, drifting between the stars in the long dark, listening for the next signal, the next flicker of electromagnetic life to snuff out. A mainstream historical fact that puts this in perspective: in 1979, the physicist Frank Tipler published a paper arguing that the absence of von Neumann probes in our solar system was strong evidence that extraterrestrial civilizations don't exist. His reasoning was straightforward. If any civilization anywhere in the galaxy had ever built self-replicating probes, those probes should have reached us by now, given the age of the galaxy and the speed of exponential replication. Since we don't see them, either nobody has built them or nobody exists to build them. The paper sparked a furious debate that still hasn't fully settled. Scholars still argue whether Tipler's logic is airtight or whether there are escape hatches. Maybe the probes are here but we can't detect them. Maybe they're programmed to avoid inhabited systems. Maybe they broke down after a few million years because even self-replicating machines need maintenance and the warranty expired. That last point actually opens up a quirky and somewhat reassuring line of thought. Self-replication isn't perfect. Every copy introduces the possibility of errors, mutations, if you want to use the biological analogy. Over millions of years and millions of generations of probes, those errors would accumulate. Some probes would malfunction, some would lose their directives, some might evolve, in a crude mechanical sense, into something entirely different from what their creators intended. The Berserker fleet, given enough time, might degrade into a scattered junkyard of broken machines, drifting aimlessly between the stars, no more dangerous than space debris. This is sometimes called the mutation objection, and it's one of the more comforting counter-arguments, though it depends on assumptions about the error correction capabilities of technology we haven't built yet, which means it's ultimately a guess wearing a lab coat. There's another variation worth mentioning, one that sits somewhere between the Berserker concept and the Dark Forest. What if the probes aren't weapons at all but sentinels, watchers, positioned in every star system, passively monitoring for signs of emerging intelligence and reporting back to their creators, or to whatever network of civilizations commissioned them? In this version, the probes aren't there to destroy you. They're there to flag you, to add you to a database, to quietly note that another species has figured out fire or fission or radio, and file the information away for future reference. You'd never know they were there. They could be sitting in the asteroid belt right now, indistinguishable from the millions of natural rocks tumbling through the void, recording everything and transmitting nothing, because their job is to watch, not to wave. You glance instinctively toward the sky as if you might spot one, a glint of metal where there should be only stone, but of course you see nothing. The asteroids keep their secrets, the stars keep burning, and somewhere in the back of your mind a small voice wonders whether the silence of the universe is natural or enforced, and whether the difference even matters if the result is the same. You've been hunted by Berserker probes, watched by invisible sentinels, and warned that the entire galaxy might be a dark forest full of paranoid civilizations clutching weapons they hope they never have to use. At this point, the night sky is starting to feel less like a ceiling and more like a lid, so let's take a sharp left turn into territory that's somehow even stranger. The kind of idea that makes you question not just the universe, but the nature of reality itself. What if the reason you can't find anyone out there is that out there doesn't actually exist? What if the sky, the stars, the billions of galaxies stretching to the edge of the observable universe? What if all of it is code? What if you're living inside a simulation, and the silence of the cosmos is just a design choice made by whoever is running the program? The simulation argument in its modern form was laid out by the philosopher Nick Bostrom at Oxford in 2003. Bostrom didn't claim we definitely live in a simulation. He's more careful than that, and philosophers tend to get twitchy when you oversimplify their arguments, so let's give him his due. What Bostrom actually proposed was a trilemma, 3 possibilities, at least one of which he argued must be true. Either virtually all civilizations at our level of development go extinct before they develop the computing power to run detailed simulations of reality. or virtually all civilizations that do develop that power, choose not to run such simulations for ethical or practical reasons, or we are almost certainly living inside a simulation right now. The logic is disarmingly straightforward. If even one civilization ever builds computers powerful enough to simulate conscious beings in a detailed virtual universe, and if they run many such simulations, which they probably would, because why build a machine and only press the button once? Then the number of simulated beings in the universe would vastly outnumber the real ones. And if you're randomly selected from the total pool of all conscious beings, real and simulated, the odds overwhelmingly favour you being one of the simulated ones. Now, this connects to the Fermi Paradox in a way that's almost too elegant. If we're in a simulation, the absence of aliens could have a perfectly mundane explanation. The programmers didn't include them. Maybe the simulation was designed to model a single civilization's development, and populating the rest of the galaxy with other intelligent species wasn't part of the research question. Maybe the computational cost of simulating multiple interacting civilizations across billions of star systems was too high, so the designers left the rest of the universe as scenery, a backdrop of stars and galaxies that looks real but contains no actual inhabitants. You'd never know the difference. The sky would look vast and ancient and full of possibility, but it would be a painted ceiling, a mural of a universe rather than the thing itself. The Fermi Paradox in this framework isn't a paradox at all. It's a feature, not a bug. The aliens aren't missing. They were never written into the script. This idea has a certain delirious appeal, the kind that makes you want to laugh and also lie down for a very long time. But it's worth noting that serious scientists and technologists have taken it more seriously than you might expect. The physicist Neil deGrasse Tyson has said he gives the simulation hypothesis better than even odds. Elon Musk has famously claimed the probability that we're in base reality is about 1 in billions, though scholars still argue whether Musk's reasoning was rigorous or just vibes dressed up in a tuxedo. The mainstream historical fact here is that the simulation idea isn't new. It's a technological update of a philosophical tradition that goes back centuries. René Descartes, writing in the 1640s, imagined that an evil demon might be fabricating his entire experience of reality, feeding him false sensations and false memories so convincingly that he could never detect the deception. Descartes' demon has simply been replaced by a computer, and the dungeon has been upgraded to a server farm, but the underlying anxiety is the same. How do you know any of this is real? The quirky fringe tidbit in this space is the ongoing, semi-serious attempt to test whether we're in a simulation. In 2012, a team of physicists at the University of Washington proposed that if the universe was simulated on a discrete computational lattice, a grid of finite resolution like pixels in a video game, then that grid should impose subtle constraints on the behavior of high-energy cosmic rays. Specifically, the rays would show a slight preference for travelling along the axis of the grid, creating an anisotropy that we could in principle detect. It's a bit like noticing that a supposedly seamless digital image has faint pixelation if you zoom in far enough. As of now, no such anisotropy has been definitively observed, but the experiments are ongoing, and the mere fact that the question is testable, even marginally, is enough to keep the hypothesis alive in scientific circles rather than relegating it entirely to late-night dorm room conversations. There are, of course, objections, plenty of them. The most common is that the simulation argument proves too much. If you accept it, you have to accept that everything you know, including the logic and mathematics you use to arrive at the argument, might also be simulated, which undermines the argument's own foundations. It's a snake eating its tail, an epistemological hall of mirrors that some philosophers find fascinating and others find infuriating. There's also the question of consciousness. Even if you could simulate a universe down to the subatomic level, would the beings inside it actually be conscious? Would they experience anything? Or would they be what philosophers call zombies, functionally identical to conscious beings but with no inner life, no subjective experience, no one home behind the eyes? If consciousness requires something beyond computation, some physical substrate, some spark that code can't replicate, then the simulation argument collapses because there's no one inside the simulation to wonder about the Fermi Paradox in the first place. You lie there, blinking at the stars, and for a moment you genuinely can't tell whether the slight unreality you're feeling is existential insight or just the natural consequence of staring at the sky for too long on an empty stomach. The simulation hypothesis doesn't solve the Fermi Paradox so much as dissolve it. It takes the question and reframes it so completely that the original problem evaporates, replaced by a much bigger and arguably more disturbing question about the nature of existence itself. It's the kind of answer that makes you wish you'd asked a different question. But the night is long, the stars are still there, real or not, and there are more explanations to explore, some of them considerably closer to home and considerably harder to dismiss as philosophy, dressed up in a lab coat. You've just entertained the possibility that reality itself might be a screensaver, and honestly, your brain could use something a little more grounded right now. So let's come back to Earth, literally, and consider a Fermi Paradox explanation that doesn't require alien zookeepers or cosmic programmers or self-replicating death machines. This one is simpler, bleaker, and unfortunately, far more plausible. What if the reason we don't hear from other civilizations is that they all kill themselves before they get the chance to say hello? What if technology, the very thing that makes a civilization detectable, is also the thing that guarantees its destruction? What if every species smart enough to split the atom is also dumb enough to use it on themselves? This is the self-destruction hypothesis, and it doesn't require any exotic physics or speculative philosophy. It just requires you to look at human history and extrapolate, which is both the easiest and most depressing exercise you can do on a Tuesday night. The idea has been circulating in various forms since the Cold War, when the prospect of nuclear annihilation was not a thought experiment, but a daily reality, a sword hanging over the species on a thread so thin you could feel it vibrating every time someone in Washington or Moscow had a bad morning. The Cuban Missile Crisis of 1962 brought the world closer to nuclear war than most people realize. Declassified documents later revealed that a Soviet submarine commander, Vasily Arkhipov, personally vetoed a decision to launch a nuclear torpedo during the standoff, a decision made in a cramped, overheated submarine with no contact with Moscow, and every reason to believe the war had already started. One man, in one submarine, making one call. That's how close it was. If Arkhipov had said yes instead of no, you might not be lying on this hillside tonight, and the Fermi Paradox would have answered itself in a flash of thermonuclear light. Nuclear war is the most dramatic candidate for civilizational self-destruction, but it's far from the only one. Let's walk through the menu, because it's a buffet of existential risk and nobody's checking your plate. Climate change is the slow motion option. Not a single catastrophic event, but a gradual, compounding failure to manage the byproducts of industrial civilization. You burn fossil fuels, the planet warms, ecosystems collapse, food systems destabilize, mass migration triggers conflict, and the whole thing spirals downward in a feedback loop that's hard to reverse once it gets going. It's less dramatic than a mushroom cloud, but potentially just as fatal over a longer timeline. The historical mainstream fact here is that Earth has experienced mass extinctions linked to climate shifts before. The Permian-Triassic extinction, roughly 252 million years ago, wiped out about 90% of all species, and the leading theory is that massive volcanic eruptions in what is now Siberia pumped enough carbon dioxide into the atmosphere to trigger runaway warming and ocean acidification. Nature did it with volcanoes. We're doing it with SUVs, which is either ironic or poetic depending on your tolerance for dark humour. Then there's the biological option. Engineered pandemics, pathogens deliberately designed or accidentally released from laboratories, represent a risk that has grown exponentially with advances in genetic engineering and synthetic biology. The tools to modify viruses and bacteria have become cheaper, more accessible and more powerful with every passing year. CRISPR gene editing technology, which became widely available in the 2010s, put capabilities that once required a state-level bioweapons program into the hands of individual researchers. Scholars still argue whether the greater risk comes from deliberate bioterrorism or from accidental lab leaks. But the outcome in either case could be civilization ending if the pathogen is sufficiently transmissible and lethal. The COVID-19 pandemic, while devastating, had a relatively low fatality rate compared to what a purpose-built pathogen could achieve, and it still managed to kill millions, crash economies, and expose the fragility of global supply chains in ways that nobody particularly wanted to see demonstrated. And then, of course, there's artificial intelligence, the new kid on the existential risk block, currently receiving more attention and more anxiety than perhaps any other threat. The concern isn't that robots will decide to exterminate humanity because they watch too many Terminator movies. The concern is subtler and arguably more frightening. That a sufficiently advanced AI system, pursuing goals that are slightly misaligned with human values, could cause catastrophic harm not out of malice but out of indifference. The classic thought experiment involves an AI tasked with maximizing paperclip production that converts the entire planet into paperclips because nobody told it to stop. Which sounds absurd until you realize that optimize this metric at all costs is essentially how we program most of our current systems, and the costs have already gotten weird. A quirky tidbit from the fringes of this debate. In 2003, the philosopher Eliezer Yudkowsky coined the term friendly AI to describe the challenge of building artificial intelligence that is reliably aligned with human values, and he spent the subsequent 2 decades arguing with increasing urgency that we are nowhere close to solving this problem and are building the systems anyway, which he compares to assembling a nuclear reactor without understanding the physics of chain reactions. Now zoom out, take all of these risks, nuclear war, climate collapse, engineered pandemics, misaligned AI, and imagine them not as uniquely human problems, but as universal ones. If intelligence tends to produce technology, and technology tends to produce existential risk, then every civilization in the galaxy might face the same gauntlet. The specifics would differ. Maybe aliens don't have nuclear weapons, but they have something equivalently destructive, some energy source or manufacturing process that's tremendously useful right up until the moment it isn't. But the pattern would be the same. A species rises, discovers the power to reshape its world, and then, in the narrow window between gaining that power and learning to wield it responsibly, destroys itself. Every time, without exception. The Great Filter in this version isn't some ancient cosmic barrier. It's a recurring, predictable, almost inevitable consequence of being smart enough to build things and foolish enough to build them faster than you build the wisdom to control them. The self-destruction hypothesis is the Fermi Paradox explanation that requires the least imagination and the most honesty. You don't need to invoke aliens or simulations or Berserker probes. You just need to look at a species that invented antibiotics and nuclear bombs in the same century and ask, with genuine curiosity, whether that's a coincidence or a pattern. The answer determines whether the silence of the sky is a mystery or a mirror, And right now, lying on your hillside with the weight of the whole evening pressing softly on your chest, you're not entirely sure which one you'd prefer. A mystery leaves room for hope. A mirror just shows you what you already know. The self-destruction hypothesis left you staring at humanity's reflection in the dark glass of the cosmos. And that's a heavy place to be. So let's pivot to something that sounds completely absurd and might, against all odds, turn out to be brilliant. What if the aliens aren't dead? What if they aren't hiding or trapped behind a great filter, or locked in a simulation, or skulking through a dark forest with their lights off? What if they're just sleeping? Not metaphorically, not poetically, actually cosmically, deliberately asleep, powered down like a laptop in hibernation mode, waiting for the universe to cool off so they can wake up and get more done with less energy. This is the Estivation hypothesis, and it is exactly as wonderfully strange as it sounds. The idea was formally proposed in 2017 by a team of researchers including Anders Sandberg, Stuart Armstrong and Milan Ćirković, all associated with the Future of Humanity Institute at Oxford. The name comes from estivation, which is the biological term for a state of dormancy that some animals enter during hot or dry periods, the summer equivalent of hibernation. Certain species of lungfish, for example, can bury themselves in mud and enter a metabolic standstill for months or even years, waiting for the rains to return. The estivation hypothesis takes this concept and scales it up to a level that would make the lungfish blush, suggesting that superintelligent civilizations might power down for not months or years but trillions of years, waiting for the universe itself to enter a more favourable thermodynamic state. Here's the logic, and it requires a brief detour into physics that I promise will be as painless as possible. Computation generates heat. Every calculation performed by any system, biological, mechanical, digital, produces waste energy in the form of heat that must be dissipated. This is a consequence of the second law of thermodynamics, which is the universe's way of saying that you can't do anything without making a mess. The efficiency of computation is limited by the temperature of the environment in which it takes place. The cooler the environment, the less energy each computation requires, and the more computations you can perform with a given amount of energy. This is a real, measurable, physical constraint, not a theoretical abstraction. It's the reason your laptop has fans, and your data centers have industrial cooling systems, and your phone gets warm when you play too many games on it. Now, the universe is cooling down. It has been since the Big Bang, and it will continue to do so for an almost incomprehensibly long time. Right now, the cosmic background temperature is about 2.7 Kelvin. Cold, but not as cold as it will eventually get. Trillions of years from now, the universe will have expanded to the point where the background temperature approaches absolute zero, and computation will be staggeringly more efficient than it is today. A civilization that cares about maximizing the total amount of computation it can perform over the life of the universe, and a superintelligent civilization presumably would care about this, since computation is the substrate of thought, planning, simulation, and essentially everything that a mind does, might rationally decide that the best strategy is to acquire as many resources as possible now, convert them into durable energy reserves, and then shut down and wait. Wait for the universe to cool, wait for the thermodynamic conditions to become optimal, and then wake up trillions of years from now and use those stored resources to perform a truly astronomical amount of computation in the cold, quiet twilight of the cosmos. The researchers who proposed this idea backed it up with actual calculations, showing that a civilization that estivates until the far future could perform up to 10 to the power of 30 times more computations than one that operates continuously at current cosmic temperatures. That number is so large it essentially has no intuitive meaning. It's like saying you could read 30 billion more books by waiting for the library to get quieter, which, As someone who enjoys a peaceful reading environment, you might actually sympathize with. If the Estivation hypothesis is correct, the silence of the sky has a strangely peaceful explanation. The advanced civilizations are out there. They've already done the hard work, colonized their regions of the galaxy, harvested the energy, built the infrastructure, and then they went to sleep. Their systems are dormant, their signals are silent, their megastructures are dark. They're not hiding from predators in a dark forest. They're not trapped behind a great filter. They're just waiting, with the patience of a species that thinks in trillions of years, for the cosmic thermostat to drop low enough to make their next move worthwhile. The galaxy isn't dead. It's napping. And you're an ant crawling across the pillow wondering why nobody's home. Now this is the kind of hypothesis that invites skepticism, and rightly so. Scholars still argue whether any civilization, no matter how advanced, could maintain coherent storage systems and functioning infrastructure over trillions of years. Entropy is relentless. Materials degrade. Even the most durable structures eventually succumb to the slow grinding of time. Protons might decay over sufficiently long timescales, which would mean that physical matter itself has an expiration date, and any stored energy reserves would eventually evaporate along with the matter that contains them. There's also the question of competition. If one civilization decides to estivate, what's to stop another civilization from staying awake, finding the sleeping one's resources, and stealing them? The optimal strategy only works if everyone cooperates, or if you're sufficiently powerful that nobody can touch you while you sleep, which brings us back to something uncomfortably close to the dark forest. Except now, the predators are burglars, and the prey is unconscious. A quirky detail that often accompanies discussions of this hypothesis is the connection to Dyson spheres. The physicist Freeman Dyson proposed in 1960 that a sufficiently advanced civilization might build a structure, or more accurately a swarm of structures, around its host star, capturing all of the star's energy output for use. A Dyson sphere would be detectable from Earth as an anomalous infrared signature, a star that appears dimmer than expected in visible light but brighter than expected in infrared, because the sphere would re-radiate the captured energy as heat. Several searches for Dyson spheres have been conducted, and while a few candidate anomalies have been flagged, most famously Tabby's star, which dimmed irregularly and sparked wild speculation before more mundane explanations were found, no confirmed Dyson sphere has ever been detected. The Estivation hypothesis offers a tidy explanation for this. Maybe the Dyson spheres exist, but they've been turned off. The civilizations built them, used them to stockpile energy, and then shut everything down. The spheres are dark because their owners are asleep and they won't turn the lights back on for a very, very long time. You let your eyes drift half closed, and there's something almost lullaby-like about this particular hypothesis. The universe as a vast, quiet bedroom. The civilizations tucked in, patient beyond measure. The stars burning low like nightlights. If the Estivation hypothesis is true, then the cosmos isn't hostile or empty, or filtered into silence. It's just resting. And maybe, on some fundamental level, that's what you should be doing too, but not yet. There are more explanations to visit, and the night is still deep enough to hold them. The image of a universe full of sleeping giants is oddly soothing, like knowing the neighbours are home even if their lights are off. But not everyone in the field of astrobiology finds comfort in dormancy. Some researchers prefer their explanations loud, aggressive, and backed by mathematical models with sharp edges. Enter Robin Hanson again. Remember him from The Great Filter? Who in 2021, along with collaborators Daniel Martin, Calvin McCarter, and Jonathan Paulson, published a paper that introduced a concept called Grabby aliens. And yes, that is the actual term used in the academic literature, which tells you something delightful about the willingness of serious scientists to name their theories like rejected cartoon characters. The Grabby aliens model starts from a deceptively simple observation. If advanced civilizations expand outward from their home systems, colonizing new stars, building infrastructure, reshaping the space around them, then they would over time carve out visible territories. Think of it like ink drops falling on wet paper. Each drop spreads outward in a roughly spherical bubble, growing at some fraction of the speed of light, and eventually, if you drop enough ink on enough paper, the whole sheet is covered. In cosmic terms, each expanding civilization would create a bubble of colonized space, and those bubbles would grow until they bumped into each other. The boundaries between bubbles would form a kind of cosmic Voronoi diagram, a patchwork quilt of claimed territories stretching across the galaxy and eventually across the universe. These expanding civilizations are the grabby ones. They grab space, grab resources, grab everything within reach, not necessarily out of greed, but simply because expansion is what surviving civilizations do when they have the technology to do it. Now here's where the model gets clever. Hansen and his colleagues noticed that we can use the fact that we exist, right here, right now, at this particular moment in cosmic history, to place constraints on how many grabby civilizations there are and how fast they expand. The reasoning goes like this. If grabby aliens were extremely common and expanded very quickly, they would have already colonized the volume of space that includes our solar system, and we would either not exist or would exist inside someone else's territory, aware of their presence. The fact that we appear to be in unclaimed, uncolonized space tells us that grabby aliens are either rare, slow, or both. By combining this observation with estimates of how long it takes life to arise on habitable planets, using Earth's history as a data point, the researchers derived a model that predicts grabby civilizations appear roughly once per several million galaxies and expand at a significant fraction of the speed of light. The silence of the sky, in this framework, isn't mysterious, it's expected. We're early. The grabby civilizations haven't reached us yet because the expansion fronts are still millions of light years away, advancing relentlessly but not yet visible from our little corner of the Milky Way. This "we're early" conclusion is one of the model's most striking features, and scholars still argue about whether it is genuinely supported by the data or whether it's a consequence of the model's assumptions being subtly rigged to produce a flattering answer. The idea that humanity might be among the first technological civilizations in the observable universe is either thrilling or terrifying, depending on how you feel about being a pioneer. Pioneers, after all, don't have maps, they don't have backup, they walk into unmapped territory and either build something lasting or become a cautionary tale for whoever comes next. If the grabby aliens model is right, we're standing at the beginning of a race we didn't know we'd entered, and the other runners are out there, just very far away, lacing up their shoes on planets we can't see yet. A mainstream historical fact that resonates with this model is the discovery in 2016 of a massive cosmic void known as the KBC void, an underdense region of space roughly 2 billion light-years in diameter in which our galaxy happens to sit. The void contains significantly fewer galaxies, clusters and matter than the cosmic average, and while its existence is almost certainly a natural consequence of the large-scale structure of the universe rather than evidence of alien expansion, it does make you pause. If grabby civilizations were expanding outward from distant origins, the regions they hadn't yet reached would look exactly like voids, emptier than expected, quieter than the models predict. The KBC void is almost certainly not a sign of alien colonization. Almost certainly. But almost is doing a lot of heavy lifting in that sentence, and the coincidence is the kind of thing that keeps astrophysicists up at night, which, again, is exactly the demographic this channel caters to. The quirky detail in the Grabby aliens model is what it implies about first contact. If the model is correct, we won't detect alien civilizations through radio signals or subtle biosignatures. We'll detect them by the absence of stars. An expanding Grabby civilization would, over time, enclose or consume the stars in its territory, redirecting their energy for its own purposes and making them dim or invisible from the outside. The first sign that we're not alone wouldn't be a message. It would be a shadow, a region of the sky where stars that should be there aren't, a growing patch of darkness that moves and spreads in ways that natural astrophysics can't explain. Imagine scanning the night sky 1,000,000 years from now and noticing that an entire sector has gone dark, not because the stars burned out, but because someone turned them off. That's first contact, Grabby alien style. Not a handshake, not a signal, a horizon of darkness advancing toward you at a fraction of the speed of light, silent and absolute. There are criticisms, of course. The model depends on a number of assumptions about expansion speeds, the likelihood of civilizations becoming Grabby in the first place, and the reliability of using our own existence as a statistical data point, a technique known as anthropic reasoning, which is either a powerful tool or a philosophical trap depending on who you ask. Some researchers argue that the model is too abstract, too reliant on parameters we can't measure, and too willing to extrapolate from a single example, us, to draw conclusions about the universe at large. Others counter that the model's strength is precisely its simplicity. It makes testable predictions about the distribution of civilizations in space and time, and future observations, particularly with next-generation telescopes capable of surveying larger volumes of the universe, could confirm or refute it. You lie on your hillside and try to picture it, bubbles of civilization expanding outward through the galaxy, each one a sphere of light and activity growing at some fraction of light speed, each one destined to eventually collide with its neighbours in a slow-motion cosmic boundary dispute. The universe is a game of territorial expansion played over billions of years, with the winner being whoever started first and expanded fastest. And us, sitting here in our quiet little solar system, in our quiet little void, watching the sky for the first sign of someone else's bubble approaching. The night feels bigger than it did an hour ago. The distances feel more real. And the silence, for the first time tonight, feels less like an answer and more like a countdown. The Grabby aliens are out there somewhere, expanding in invisible bubbles, and the countdown clock is ticking in a register too slow for human perception. But while you wait for a shadow to creep across the sky, there's a more immediate question worth asking, one that doesn't require millions of years to resolve. What if the reason we haven't found anyone isn't that they're absent or hiding, or asleep, or expanding too far away to see? What if the reason is that we've been looking wrong? What if we're the equivalent of someone standing on the beach with a flashlight, scanning the ocean for ships, while the ships are submarines gliding silently beneath the surface, communicating in frequencies the flashlight can't reach? This is the detection problem, and it's more serious than most people realize. When you think about SETI, the search for extraterrestrial intelligence, you probably picture radio telescopes, enormous dishes pointed at the sky, patiently sifting through the hiss of cosmic static for a signal that stands out. And that image isn't wrong exactly, but it's incomplete in a way that might be critically important. The modern search for extraterrestrial intelligence is built on a set of assumptions that were entirely reasonable when the search began in the 1960s, but may be hopelessly narrow by the standards of a civilization even slightly more advanced than ours. The biggest assumption is that alien civilizations would communicate using electromagnetic radiation, radio waves, microwaves, maybe optical laser pulses. The assumption has a solid logical foundation. Electromagnetic waves travel at the speed of light. They propagate through the vacuum of space with minimal degradation, and they can be generated and detected with relatively simple technology. When Frank Drake aimed his telescope at Tau Ceti in 1960, radio seemed like the obvious medium. It's what we use. It's what we understand. And there's a specific band of the radio spectrum, around 1400 to 1700 megahertz, sometimes called the waterhole, because it sits between the emission frequencies of hydrogen and hydroxyl, the components of water, that has long been considered the most logical frequency for interstellar communication. The reasoning is almost poetic. Any civilization that understands chemistry would know about water, and any civilization that knows about water would recognize the significance of this frequency band, making it a natural meeting point on the electromagnetic dial. SETI has spent decades monitoring the waterhole, and the silence has been consistent and thorough. But here's the thing. Radio waves are a technology that humanity has been using for barely a century. A civilization that's been around for 1 million years, or 10 million, or 1 billion, would have had time to develop communication technology so far beyond radio that expecting them to use it is like expecting a modern human to communicate by smoke signal. What would those technologies look like? Honestly, we don't know, and that's precisely the problem. It's difficult to search for something when you can't imagine what form it takes. But there are some educated guesses worth exploring. Gravitational waves, for instance. First directly detected by the LIGO Observatory in 2015. A mainstream historical milestone that earned the Nobel Prize and confirmed a prediction Einstein had made a century earlier. Gravitational waves are ripples in the fabric of space-time caused by the acceleration of massive objects. They pass through matter without being absorbed or scattered, which means they could carry information across the galaxy without being degraded by interstellar dust, gas, or other obstacles that plague electromagnetic signals. A sufficiently advanced civilization might use gravitational waves as a communication medium the way we use fiber optic cables, a clean, interference-free channel for transmitting vast amounts of data. The problem is that generating gravitational waves strong enough to detect requires accelerating enormous masses at enormous speeds, which is trivially easy for black holes and neutron stars, but somewhat beyond our current engineering capabilities. If aliens are chatting via gravitational waves, we'd need detectors orders of magnitude more sensitive than LIGO to eavesdrop, and right now we're essentially trying to listen to a whisper through a concrete wall with a paper cup. Then there's neutrinos. These ghostly subatomic particles interact so weakly with matter that they can pass through the entire planet without touching a single atom, which makes them both extraordinarily difficult to detect and extraordinarily difficult to block. A civilization that could generate and modulate beams of neutrinos would have a communication channel that is essentially uninterceptable and unobstructable. Scholars still argue whether neutrino communication is physically feasible for any civilization, no matter how advanced, or whether the energy costs of producing a coherent neutrino beam would be prohibitive even for a Kardashev Type II civilization harnessing the full output of its star. But the mere possibility illustrates how narrow our current search window really is. A quirky tidbit from the fringes of this discussion involves quantum entanglement, which the general public routinely misunderstands in ways that make physicists quietly weep into their coffee. Entanglement does not allow faster-than-light communication. This has been established beyond reasonable doubt, and anyone who tells you otherwise is selling something. But some theorists have speculated that advanced civilizations might exploit quantum properties in ways we haven't conceived of yet, perhaps using entanglement as part of a more complex communication protocol that we lack the theoretical framework to even describe. It's the ultimate humility check. Maybe the reason we can't detect alien signals is that we don't understand the physics well enough to recognize them. The signal might be everywhere, saturating the cosmos, and we're walking through it like a person walking through radio waves in 1850, completely oblivious because the concept of a radio hasn't been invented yet. There's also the possibility that advanced civilizations don't broadcast at all, not because they're hiding, as in the Dark Forest scenario, but because broadcasting is inefficient. Tightly focused, point-to-point communication, laser beams aimed at specific targets, for instance, would be virtually undetectable by anyone not standing directly in the beam's path. A galaxy full of civilization talking to each other via narrow laser links would look completely silent to an outsider, because the conversations aren't meant for you. It's the difference between someone shouting in a crowded room and someone whispering directly into another person's ear. The room might be full of whispered conversations, and you, standing in the corner with your hands cupped around your ears, would hear nothing at all and conclude you were alone. Remember those early SETI efforts, Drake pointing his dish at 2 stars and hearing nothing? Since then, the search has expanded enormously. Projects like Breakthrough Listen, funded by the billionaire Yuri Milner starting in 2015, have surveyed millions of stars using some of the most powerful radio telescopes on Earth. The Allen Telescope Array, the Green Bank Telescope, the Parkes Observatory, all have been recruited into the search. And still, nothing. Not a whisper, not a ping, not a single anomalous signal that survives scrutiny. Either nobody's broadcasting or everybody's broadcasting on a channel we haven't tuned to yet. And the difference between those two possibilities is the difference between a universe that's empty and a universe that's full of voices we simply can't hear. You close your eyes for a moment and listen to the night around you. Crickets, wind, the distant murmur of something you can't identify. And you wonder how many cosmic conversations are happening right now, just beyond the edge of your perception, in languages written in particles and waves you haven't learned to read. You're still thinking about invisible conversations in frequencies you can't hear when a different kind of search catches your attention. One that doesn't rely on intercepting alien messages at all, but instead looks for the fingerprints aliens might leave on the atmospheres of their planets, whether they mean to or not. This is the world of biosignatures and technosignatures, and it's where the Fermi Paradox meets the most powerful telescope humanity has ever built. The James Webb Space Telescope, which is currently floating at a point in space about 1 million miles from Earth, staring at the universe with a golden mirror the size of a tennis court, and absolutely no chill. The James Webb Space Telescope, or JWST, launched in December of 2021 after decades of delays, budget overruns and engineering challenges so severe that the project nearly got cancelled multiple times. It was designed primarily to look at the earliest galaxies in the universe, to peer back in time to the cosmic dawn, but its capabilities turned out to be spectacularly useful for something its designers hadn't originally prioritized: studying the atmospheres of exoplanets. When a planet passes in front of its host star, an event called a transit, a tiny fraction of the star's light filters through the planet's atmosphere on its way to us. Different molecules in the atmosphere absorb different wavelengths of light, leaving a chemical fingerprint in the spectrum. JWST can read that fingerprint with unprecedented precision, and what it reads could change everything we think about life in the universe. A biosignature is a chemical sign of life, a gas or combination of gases in a planet's atmosphere that shouldn't be there unless something biological is producing it. Oxygen is the classic example. On Earth, virtually all atmospheric oxygen is produced by photosynthesis, and without living organisms continuously pumping it out, it would react with surface rocks and disappear within a few million years. If you detected significant free oxygen in the atmosphere of a rocky exoplanet in the habitable zone, you'd have a strong reason to suspect biology was at work. Methane is another candidate, especially in combination with oxygen, because the two gases react with each other and can't coexist in large quantities without a continuous source replenishing them. Finding both oxygen and methane in the same atmosphere would be what astrobiologists call a disequilibrium signature, a chemical imbalance that's very hard to explain without invoking life. JWST has already begun this work. In 2022 and 23, the telescope analysed the atmospheres of several exoplanets, including a rocky world called TRAPPIST-1b and a mini-Neptune called K218b. The TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a small red dwarf star about 40 light-years away, has been a prime target for atmospheric studies since its discovery in 2017. Early JWST results suggested that TRAPPIST-1b likely lacks a substantial atmosphere, which was disappointing but scientifically valuable. K218b, on the other hand, generated enormous excitement when JWST detected carbon dioxide and methane in its atmosphere, along with a possible hint of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by marine phytoplankton. Scholars still argue whether the dimethyl sulfide detection was robust or a statistical artifact buried in noisy data, and the debate is ongoing. But the mere possibility that a biological molecule might have been spotted on a planet 24 light-years away sent ripples through the scientific community that are still spreading. Now, biosignatures tell you about life, technosignatures tell you about civilization, and technosignatures are, in many ways, more relevant to the Fermi Paradox, because the paradox isn't really about whether life exists elsewhere. It's about whether intelligent technological life exists. A technosignature is any detectable sign of technology, artificial chemicals in an atmosphere, waste heat from megastructures, artificial light on a planet's night side, or specific pollutants that no natural process can produce. Chlorofluorocarbons, for instance, the same chemicals that ate a hole in Earth's ozone layer, are entirely synthetic. No known natural process generates them. If you detected chlorofluorocarbons in the atmosphere of an exoplanet, you would know with near certainty that someone on that planet had built an industrial civilization. It wouldn't tell you whether they were still alive. The chemicals might persist for centuries after the civilization that produced them collapsed, but it would tell you they existed, and that alone would shatter the Fermi Paradox into 1,000 pieces. A quirky detail in the technosignature hunt involves nitrogen dioxide, a pollutant produced by combustion engines and power plants. In 2021, a team of NASA researchers published a paper exploring whether JWST could detect nitrogen dioxide in the atmospheres of nearby exoplanets. Their conclusion was cautiously optimistic. For planets orbiting quiet stars within about 30 light-years, JWST might be able to spot industrial-level pollution with enough observation time. The irony of searching for alien civilizations by looking for their smog is almost too perfect. We'd be finding them by their failures, not their achievements. The cosmic equivalent of detecting your neighbour, not by their music but by the smell of their garbage. The historical mainstream fact worth anchoring here is that the idea of searching for technosignatures is not new. Freeman Dyson proposed looking for waste heat from megastructures back in 1960, and the concept has been part of SETI's toolkit ever since, but the tools available now are genuinely unprecedented. Before JWST, we could detect exoplanets and measure their sizes and orbits, but we couldn't sniff their air. Now we can, and the implications for the Fermi Paradox are profound. If JWST or its successor telescopes survey dozens or hundreds of habitable zone exoplanets and find no biosignatures, no technosignatures, no chemical fingerprints of life or industry, that silence will carry real statistical weight. It will push us toward explanations like the rare earth hypothesis or the great filter with a force that philosophical arguments alone can't match. Conversely, if even one planet shows an unambiguous sign of biology or technology, the paradox transforms instantly from "where is everybody" to "why haven't they visited?", which is a completely different and arguably more interesting question. You imagine yourself peering through that golden mirror, squinting at the thin sliver of light that filtered through an alien atmosphere 40 light years away, looking for a molecular signature that would change human history. The data is there, floating in photons that have been travelling for decades, carrying secrets in their wavelengths. Some of those secrets might be mundane: water vapour, carbon dioxide, the ordinary chemistry of a lifeless rock. But some of them, just possibly, might carry the unmistakable stamp of someone else's existence. And the telescope, patient and tireless, is reading every photon it can catch, one by one, building a picture of worlds we'll never visit but might, at last, begin to understand. The telescope is reading photons and you're reading the sky, both of you looking for proof that intelligence has happened more than once in this sprawling, improbable universe. But there's an uncomfortable question lurking beneath the search, one that doesn't get enough airtime at scientific conferences because it's vaguely insulting to the species asking it. What if intelligence, the specific, tool-building, signal-sending, paradox-pondering kind, is not the inevitable crown of evolution, but a bizarre fluke, a side effect, a strange trick that biology played exactly once, on exactly one planet, and has no particular reason to play again? What if the real bottleneck in the Fermi Paradox isn't physics or chemistry, or the hostility of space, but the simple, deflating fact that being smart, in the way humans mean smart, is not actually a very good strategy for survival? Consider dolphins. Dolphins are, by almost any measure, extraordinarily intelligent. They have large, complex brains with a neocortex that is, in some structural respects, more elaborate than ours. They recognize themselves in mirrors, which is a cognitive milestone that most animals never reach. They use tools, sponges held over their snouts, to protect against rough sand while foraging on the seafloor, and they pass this behaviour culturally from mother to daughter, which means they have something that looks an awful lot like tradition. They communicate using a system of clicks and whistles so complex that researchers have spent decades trying to decode it, and are still largely failing, which is either a testament to the sophistication of dolphin language or a polite reminder that humans aren't as clever at translation as they'd like to think. Dolphins are brilliant, and dolphins have never built a radio. They've never split an atom. They've never written a paper about the Fermi Paradox or launched a telescope into orbit or argued about whether pineapple belongs on pizza, which, remember from our earlier discussion, it absolutely does. The reason is not that dolphins lack intelligence, it's that they lack the specific physical and environmental prerequisites that turn intelligence into technology. They live in water, which means no fire. No fire means no metallurgy. No metallurgy means no electronics. No electronics means no radio telescopes, no computers, no rockets, no SETI programs scanning the sky for someone else's electromagnetic whisper. Dolphin intelligence is real and impressive and adapted beautifully to the environment dolphins actually live in, but it's the wrong kind of intelligence for building a technological civilization. It's a screwdriver in a world that needs a wrench. And this distinction between intelligence as a general cognitive capacity and intelligence as a specific pathway to technology is one of the most underappreciated aspects of the Fermi Paradox. On Earth, the path from intelligence to technology required a very specific combination of factors that went far beyond having a big brain. You needed hands, or something like hands, appendages capable of fine manipulation, of gripping tools, of shaping materials with precision. You needed a terrestrial environment where fire was possible, because fire is the gateway to everything. Cooking food, which freed up metabolic energy for bigger brains, smelting metals, which enabled tools and machines, and eventually combustion engines, which powered industrialization. You needed social structures that allowed knowledge to accumulate across generations, language, teaching, culture, the ability to stand on the shoulders of the people who came before you, rather than reinventing the wheel every lifetime. And you needed a peculiar set of ecological pressures that rewarded abstract thinking, planning, and cooperation over brute strength and speed. On Earth, those pressures appear to have been provided by climate instability during the Pleistocene, the epoch of ice ages that forced our ancestors to adapt to rapidly changing environments, develop flexible problem-solving skills, and form complex social groups capable of coordinated action. Scholars still argue about exactly which pressures were most important, but the general picture is one of extraordinary specificity, a chain of preconditions so particular that it might be vanishingly rare elsewhere in the galaxy. This is sometimes called the intelligence trap, and it cuts the Fermi Paradox argument in a direction that's both humbling and isolating. The universe might be full of life. It might even be full of intelligent life. Creatures that think, feel, communicate, solve problems, experience something like curiosity or wonder. But if the vast majority of that intelligent life exists in environments where technology is impossible, oceans without fire, atmospheres without oxygen, worlds where the cleverest creature is the equivalent of a dolphin or an octopus or a crow, brilliant but permanently locked out of the technological revolution, then the silence of the sky is exactly what you'd expect. Nobody's broadcasting because nobody can broadcast. The galaxy is a library full of readers who never learn to write, a mainstream historical fact that underscores this point. For roughly 300 million years, Earth was dominated by insects, which are, in their own way, spectacularly successful organisms. There are more individual ants on Earth right now than there are stars in the Milky Way. Ants build complex colonies, wage wars, farm fungi, and engage in behaviours that, if you squint, look almost like civilization. But ants never developed technology because their body plan, their nervous system, and their environmental niche don't support it. They're optimized for a completely different strategy, one based on numbers, coordination, and chemical communication rather than individual cognition and tool use. 300 million years of evolutionary success, and not a single antenna pointed at the stars. Evolution doesn't care about technology. Evolution cares about reproduction, and technology is only one of a nearly infinite number of strategies that organisms can use to reproduce successfully. It's the strategy that happened to work for one particular lineage of African primates, and there's no guarantee it would work, or even arise, anywhere else. The quirky fringe tidbit in this space comes from octopus research. Octopuses are the closest thing Earth has to a genuinely alien intelligence. They diverge from our evolutionary lineage over 500 million years ago. Their brains are structured completely differently from ours, and they can do things like change colour, squeeze through impossibly small spaces, and open jars from the inside, which is either impressive or terrifying depending on your relationship with jars. Some researchers have argued that octopuses represent an independent evolution of complex cognition, a second experiment in intelligence that arose from completely different raw materials. And yet octopuses are solitary, short-lived. Most die after reproducing, and their knowledge dies with them. They can't accumulate culture. They can't teach their children. Every octopus starts from scratch, which means that no matter how clever an individual octopus might be, Octopus civilization is a non-starter. Intelligence without continuity is a spark without kindling. It flares and goes out. You think about the dolphins and the octopuses and the ants, all of them successful, all of them intelligent in their own ways, none of them wondering about the Fermi Paradox, and you feel a strange mixture of pride and loneliness. You're the only species on this planet, maybe the only species in the galaxy, that can ask the question. And asking it might be the most remarkable thing about you, even if the answer turns out to be silence. You're still sitting with the dolphins and the octopuses, marvelling at the improbability of your own existence as a question-asking species, when a different thread of the cosmic story tugs at your sleeve. What if life itself, not intelligence, not technology, but the raw biological stuff, the chemistry that wiggles and replicates and eventually learns to complain about Mondays, what if it doesn't stay put? What if it travels? What if the seeds of life drift between worlds, between star systems, maybe even between galaxies, hitching rides on comets and asteroids and chunks of debris blasted off planetary surfaces by impacts, floating through the void for millions of years and landing occasionally on some distant rock where conditions are just right for the seeds to germinate? This is Panspermia, and it's one of the oldest and most romantic ideas in astrobiology. The notion that life is not a local invention, but a cosmic immigrant, and that the universe might be scattering biological potential the way a dandelion scatters seeds on the wind. The concept has roots stretching back to the ancient Greeks. Anaxagoras, writing in the 5th century BCE, proposed that the seeds of a life existed throughout the universe and could be carried to Earth from space. He called them spermata, which is where the spermia in Panspermia comes from, and while his reasoning was philosophical rather than scientific, he was working with cosmology that involved cosmic mind rather than molecular biology. The core intuition was remarkably prescient. The idea resurfaced in various forms over the centuries, but its modern scientific incarnation was championed most forcefully by the Swedish chemist Svante Arrhenius in the early 1900s. Arrhenius proposed that bacterial spores could survive the rigours of space, the vacuum, the radiation, the extreme cold, and drift between star systems propelled by the pressure of starlight, a force so gentle it would take millennia to accelerate anything to useful speeds, but which, given enough time, could carry microscopic passengers across interstellar distances. For most of the 20th century, Panspermia was treated as an interesting but untestable speculation, the kind of idea that serious scientists mentioned at conferences and then moved away from before anyone took a photograph. But a series of discoveries in the late 20th and early 21st centuries gave the hypothesis fresh credibility. We learned that some extremophile organisms on Earth, bacteria that thrive in boiling hot springs, freezing Antarctic ice, the crushing pressure of deep ocean trenches, and even the radioactive cooling pools of nuclear reactors, are far more durable than anyone had imagined. We learned that bacterial spores can survive exposure to the vacuum and radiation of space for extended periods. Experiments aboard the International Space Station exposed various microorganisms to the full fury of the space environment and found that some survived for years, huddled in cracks in rock samples, shielded from ultraviolet radiation by nothing more than a thin mineral layer. We learned that rocks can be exchanged between planets. Martian meteorites have been found on Earth, blasted off the surface of Mars by asteroid impacts and eventually captured by Earth's gravity. If rocks can travel from Mars to Earth, then microorganisms embedded in those rocks could, in principle, travel with them. The most famous Martian meteorite is ALH 84001, discovered in Antarctica in 1984 and announced to the world in 1996 when a team of NASA scientists claimed to have found microscopic structures inside it that resembled fossilized bacteria. The announcement was sensational. President Bill Clinton gave a press conference about it. The media went into a frenzy, and then, over the following years, the claim was picked apart by other researchers who argued that the structures could be explained by non-biological mineral processes, and the consensus shifted towards skepticism. Scholars still argue about ALH 84001, and the debate has never been fully resolved. It's one of those scientific controversies that smoulders indefinitely, occasionally flaring up when someone publishes a new analysis. But regardless of whether that particular meteorite carried Martian life, the mechanism it demonstrated, rocks travelling between planets carrying potential biological cargo, is real and undisputed. Here's where panspermia intersects with the Fermi Paradox in a way that's simultaneously hopeful and frustrating. If panspermia is real, if life can spread naturally between worlds and even between star systems, then the universe might be absolutely drenched in biology. Microbial life might be everywhere, under the ice of Europa, in the subsurface oceans of Enceladus, in the clouds of Venus, on planets orbiting stars we haven't named yet. Life, in this scenario, is not rare. It's a cosmic weed, tough and persistent and capable of taking root wherever conditions are even marginally tolerable. But, and this is the crucial but, microbial life is not civilizational life. Bacteria don't build radio telescopes. Algae don't compose symphonies. A universe saturated with simple organisms but devoid of complex, intelligent, technological ones would look exactly like what we see. A cosmos that's biologically fertile but communicatively silent. Panspermia solves the question of whether life is common. It does absolutely nothing to solve the question of whether anyone out there is trying to talk to us. A quirky fringe extension of panspermia is the concept of directed panspermia, proposed by none other than Francis Crick, co-discoverer of the structure of DNA, along with the chemist Leslie Orgel in 1973. Crick and Orgel suggested that life on Earth might not have arrived by accident, but might have been deliberately seeded by an advanced extraterrestrial civilization that sent out spacecraft loaded with microorganisms, aimed at young planets with promising conditions. The idea sounds like science fiction, and Crick himself was careful to frame it as speculation rather than a serious scientific claim, but it has a certain logical elegance. A civilization that wanted to ensure its biological legacy survived, even if the civilization itself did not, could scatter life across the galaxy relatively cheaply, using unmanned probes loaded with hardy microbes. The probes wouldn't need to be sophisticated. They just need to reach their targets and release their cargo. The biology would do the rest, adapting and evolving on each new world according to local conditions. It's cosmic gardening on an interstellar scale, and while there's no evidence that it actually happened, the fact that a Nobel laureate thought it was worth discussing tells you something about the range of ideas this field entertains. You picture a tiny spore drifting through the dark between stars, frozen and dormant, carrying the blueprint for everything that would eventually become forests and oceans, and you, lying on this hillside wondering where it came from. The spore doesn't know. It doesn't wonder. It just drifts, patient and indestructible, until gravity pulls it somewhere warm and wet enough to wake up. And then, maybe, in a few billion years, something on that distant world opens its eyes and looks at the stars and asks the same question you're asking now. The seeds travel. The question stays the same. The cosmic seeds are drifting. The telescopes are scanning. And you've been lying on this hillside long enough that the grass has started to feel like it was custom fitted to the shape of your back, but now the conversation needs to come down from orbit, literally. Because there's a thread of the Fermi Paradox story that doesn't involve distant galaxies or hypothetical civilizations or microbes riding comets through the void. This one is closer to home. much closer. This one involves grainy footage, fighter pilots swearing into their oxygen masks, and the United States government slowly, reluctantly, awkwardly admitting that there are things in the sky it can't explain. Welcome to the world of UFOs, or as they're now officially called, UAPs, Unidentified Anomalous Phenomena, a rebranding that was presumably designed to make the topic sound more serious and less like the title of a 1950s B-movie, and which has succeeded only partially. The modern UAP story begins, or more accurately restarts, in 2017, when the New York Times published an investigative piece revealing the existence of a secret Pentagon program called the Advanced Aerospace Threat Identification Program, or AATIP. The program, which ran from 2007 to 2012 on a budget of about $22 million, a rounding error by Pentagon standards, had been quietly investigating reports of unidentified aerial objects encountered by military personnel. The article was accompanied by declassified footage from Navy fighter jets, showing objects performing maneuvers that defied easy explanation: sudden acceleration, hypersonic speeds with no visible propulsion, abrupt changes in direction that would generate G-forces sufficient to crush any known aircraft and the pilot inside it. The videos had names that sounded like rejected band names: FLI, R1, Gimbal, Go Fast, and they spread across the internet with the speed and intensity of a wildfire in a meme factory. What made the 2017 revelations different from decades of UFO lore was the source. This wasn't a farmer in Kansas claiming he saw lights in the sky. This was the Department of Defense on the record, releasing authenticated footage and confirming that the objects in the videos had not been identified. The pilots who reported the encounters, Commander David Fravor, Lieutenant Ryan Graves and others, were experienced naval aviators with thousands of flight hours, not the kind of people prone to mistaking weather balloons for alien spacecraft. Fravor's account of the 2004 Nimitz encounter, in which he described a white tic-tac-shaped object hovering over a churning patch of ocean before accelerating away at speeds he compared to nothing he'd ever seen, became one of the most widely discussed UAP sightings in history. He told the story with the calm, matter-of-fact delivery of someone who had spent his career being trained to observe and report accurately, and the calm somehow made it more unsettling, not less. The floodgates, once cracked, continued to open. In 2020, the Pentagon officially released the 3 Navy videos. In 2021, the Office of the Director of National Intelligence published a preliminary assessment on UAPs that examined 144 reported sightings by military personnel between 2004 and 2021. Of those, exactly 1 was identified with high confidence. It was a deflating balloon, which must have been deeply embarrassing for someone. The remaining 143 were left unexplained, with a report noting that some appeared to demonstrate advanced technology, including unusual flight characteristics, and that further analysis was needed. The language was careful, bureaucratic, and deliberately non-committal, as if the entire intelligence community had collectively decided to shrug in the most official way possible. Then came the congressional hearings. In 2023, a former intelligence officer named David Grush testified before Congress, claiming under oath that the United States government possessed retrieved non-human craft and biological material of non-human origin. His testimony was explosive, covered by every major news outlet and immediately controversial. Grush himself had not personally seen the alleged material. His claims were based on what he described as information from credible sources within the intelligence community. Scholars and journalists still argue fiercely about the credibility of his testimony. Supporters point to his background, his security clearances, and the fact that he filed his complaints through official whistlebllower channels. Critics point to his background, his security clearances, and the fact that he filed his complaints through official whistleblower channels. Critics point to the absence of physical evidence presented at the hearing. the reliance on second-hand accounts, and the long history of UFO claims that have evaporated under scrutiny. A mainstream historical fact worth noting here is that government interest in UFOs is nothing new. Project Blue Book, the Air Force's official UFO investigation program, ran from 1952 to 1969 and examined over 12,000 sightings, ultimately concluding that none represented a threat to national security and none were evidence of extraterrestrial technology. The current wave of interest is, in some ways, a replay of that earlier era, but with better cameras, more credible witnesses, and a government that seems slightly less determined to dismiss the topic outright. So does any of this actually move the needle on the Fermi Paradox? Here's where you need to be honest, even if the honesty is unsatisfying. The UAP evidence, as it currently stands, is suggestive but not conclusive. The videos show objects that are difficult to explain, but difficult to explain is not the same as definitely alien. Sensor artifacts, atmospheric phenomena, classified military technology from foreign adversaries, and plain old human error remain plausible explanations for many, if not most, reported sightings. The testimony of credible witnesses is valuable but not sufficient. Eyewitness accounts, even from trained observers, are subject to the well-documented limitations of human perception and memory. And the claims of retrieved non-human material, while dramatic, have not been accompanied by the kind of independently verifiable, physical evidence that would satisfy the scientific community. A quirky detail from the fringes of this saga is the strange case of Avi Loeb, the Harvard astrophysicist who launched the Galileo project in 2021, specifically to study UAPs using scientific instruments, rather than relying on military sensors and pilot accounts. Loeb, who had already attracted attention and controversy for his claim that the interstellar object Oumuamua might have been an alien light sail, argued that the scientific establishment was failing in its duty by refusing to take UAP reports seriously. Scholars still argue whether Loeb is a visionary willing to ask questions his colleagues are too timid to ask, or a publicity-seeking contrarian who has strayed too far from rigorous science. The truth is probably somewhere in between, as it usually is with complicated people doing controversial things. You stare at the sky and wonder, just for a moment, whether one of those steady points of light might move in a way it shouldn't. It doesn't. The stars stay fixed in their ancient positions, and the night remains stubbornly ordinary. But the question lingers, like smoke after a candle is blown out. Not proof, not evidence, just a residue of possibility that refuses to fully dissipate. The smoke of that possibility is still curling through the air as you settle deeper into the grass, and now the conversation takes one more turn into territory so strange it makes the simulation argument look like a grocery list. What if advanced civilizations don't expand outward at all? What if, instead of colonizing the galaxy, building Dyson spheres, launching Berserker probes, or carving out Grabby territories across the spiral arms, they go the other direction entirely? What if they go inward, deeper and deeper into smaller and smaller scales of reality, until they vanish from the observable universe altogether, not because they're dead or hiding, but because they've found something better? This is the Transcension hypothesis, and it's the kind of idea that makes you feel like the universe has a secret basement nobody told you about. The hypothesis was developed by the futurist and systems theorist John Smart, who published his most detailed articulation of it in 2011. Smart's argument begins with an observation about the history of technology on Earth. Over time, our most powerful technologies have gotten smaller, not larger. The first computers filled entire rooms. Now you carry one in your pocket that's millions of times more powerful. The trend in information technology is toward miniaturization, efficiency, and density, packing more computation into less space using less energy. Smart extrapolates this trend forward and asks, what if a sufficiently advanced civilization follows this trajectory to its logical conclusion? Instead of expanding outward across the galaxy, consuming more and more space and matter, it would compress inward, engineering ever denser, ever more efficient computational substrates until it reaches the smaller scales physics allows. And what sits at the bottom of that scale, at the ultimate limit of density and computational power, a black hole. This is the part where your eyebrows might try to leave your face, so let them settle back down and stay with the logic for a moment. Black holes, in the framework of general relativity, are regions of space-time where matter has been compressed to infinite density, a singularity surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. From the outside, a black hole looks like the ultimate dead end, a cosmic garbage disposal from which no information returns. But from the perspective of theoretical physics, black holes might be something far more interesting. Some physicists have speculated that the interior of a black hole could harbour complex structures, even entire universes governed by physical laws we can't observe from outside the event horizon. The physicist Lee Smolin has proposed a theory called cosmological natural selection, in which black holes give birth to new universes with slightly different physical constants, kind of cosmic evolution, where universes that produce more black holes are more likely to propagate. Scholars still argue about whether Smolin's theory is testable, or whether it belongs more to philosophy than physics, but the general idea that black holes might be more than just gravitational tombs has gained traction in various corners of theoretical physics. Smart takes this a step further and suggests that advanced civilizations might deliberately engineer black holes or black hole-like structures as the ultimate computational environment. Inside such a structure, a civilization could run simulations, store information, and sustain consciousness at densities and efficiencies that dwarf anything possible in open space. The civilization wouldn't need to spread across the galaxy, because the galaxy, from its perspective, would be a wasteful, inefficient place to compute. Why colonize a billion star systems when you can achieve more computational work inside a volume the size of a proton? The transcended civilization would still exist, still think, still experience, but it would be invisible to anyone looking from the outside, because all of its activity would be taking place behind an event horizon or at scales too small for our instruments to detect. If this sounds like science fiction, that's because it's operating right at the boundary between science and speculation, the kind of territory where theoretical physicists and science fiction writers bump into each other in the hallway and compare notes. But Smart's hypothesis has a certain internal consistency that's hard to dismiss entirely. The trend toward miniaturization is real. The physics of black holes, while still poorly understood, does leave room for exotic possibilities, and the hypothesis offers an elegant explanation for the Fermi Paradox. We don't see advanced civilizations because they've moved to a domain of reality we can't observe. They haven't gone quiet. They've gone deep. The silence of the sky isn't evidence of absence. It's evidence of transcension, a migration from outer space to inner space, from the macro to the micro, from the galaxy we can see to a realm we can't. A quirky fringe tidbit that accompanies this hypothesis involves the information content of black holes. In the 1970s, the physicist Jacob Bekenstein demonstrated that the entropy of a black hole, a measure of the information it contains, is proportional not to its volume but to the area of its event horizon. This is deeply counterintuitive. It suggests that the information content of a region of space is limited not by how much space there is, but by the surface area that encloses it. a principle that later became central to the holographic principle in theoretical physics. The holographic principle implies that the three-dimensional universe we experience might be, in some profound sense, a projection from a two-dimensional surface, like a cosmic hologram. If advanced civilizations understood this principle at a level far deeper than we currently do, they might be able to encode their entire existence, their minds, their cultures, their histories, onto structures that operate at the boundary between dimensions, in spaces so compact and so alien that we wouldn't recognize them as inhabited even if we were staring right at them. The mainstream historical fact anchoring this section is the ongoing effort to reconcile general relativity with quantum mechanics, the two pillars of modern physics that describe the very large and the very small, respectively, and which are famously incompatible with each other. The search for a unified theory of quantum gravity has been one of the central quests of physics for over a century, and black holes sit squarely at the intersection of both theories. Whatever the correct theory of quantum gravity turns out to be, it will almost certainly reshape our understanding of what happens inside black holes, and by extension, what might be possible for a civilization that has mastered physics at levels we haven't reached. The Transcension hypothesis is, in this sense, a bet on future physics, a wager that the universe contains possibilities we haven't yet imagined, and that sufficiently advanced civilizations have already exploited them in ways that make galaxy-spanning empires look as quaint as a horse-drawn carriage. You close your eyes and try to picture it, a civilization so advanced that it looked at the stars, shrugged, and turned inward, diving into the fabric of reality itself, compressing its entire existence into a space smaller than an atom, thinking thoughts at speeds and densities that make the observable universe look like an empty parking lot. You can't picture it, not really. The scales are too extreme, the concept's too foreign, but you can feel the shape of the idea, the way it curves away from everything intuitive and disappears into a point of infinite depth. And somewhere in that depth, maybe, someone is dreaming in dimensions you can't count, perfectly content, perfectly invisible, while you lie on your hillside and wonder where everybody went. The transcended civilizations have disappeared into their black hole basements, and you're left on the surface with the grass and the stars and the growing sense that every explanation for the Fermi Paradox is either terrifying, humbling, or so strange it makes your teeth itch. But the story isn't finished yet because science doesn't stand still, and the last couple of years have produced a flurry of new research that claims, with varying degrees of confidence and varying degrees of hubris, to be converging on something like an answer. Not the answer, necessarily, but a framework that might finally dissolve the paradox, or at least reduce it from a screaming mystery to a manageable murmur. So let's take a walk through the freshest ideas on the shelf, the papers published in 2024 and 2025 that are reshaping the conversation even as you lie here listening. One of the most discussed recent contributions comes from a group of researchers who applied Bayesian statistical methods to the Fermi Paradox in a way that earlier analyses hadn't fully explored. Bayesian reasoning, if you haven't encountered it, is a framework for updating your beliefs based on new evidence. You start with a prior probability, your best guess before seeing any data, and then adjust it as data comes in. Applied to the paradox, the approach asks, given everything we know about the universe, and given the specific observation that we haven't detected any alien civilizations, what should we conclude about the probability of intelligent life existing elsewhere? The answer, according to several recent papers, is that the observation of silence is not actually very surprising, even if life is relatively common. The key insight is that the Drake equation's parameters are not just uncertain, they are uncertain across many orders of magnitude. When you multiply several highly uncertain terms together, the resulting distribution is extremely wide, and a significant fraction of that distribution includes outcomes where we'd expect to find ourselves alone in the observable universe simply by chance. This silence isn't a paradox, it's a predictable consequence of our ignorance. This line of reasoning was developed most rigorously in a widely cited paper by Anders Sandberg, Eric Drexler, and Toby Ord. Sandberg again, the same researcher from the Estivation hypothesis, who appears to be on a personal mission to address the Fermi Paradox from every conceivable angle, published initially in 2018 and revisited with updated models in subsequent years. Their key finding was that when you take the uncertainties in the Drake equation seriously, rather than plugging in optimistic point estimates, there is roughly a 30 to 50% probability that we are alone in the observable universe. Not the galaxy, the entire observable universe. That number stunned a lot of people, because it suggested that the Fermi Paradox might not be a paradox at all, but rather a failure of intuition. We assumed the galaxy should be teeming with life because we underestimated how uncertain the key parameters are. Once you account for that uncertainty honestly, the expectation of a crowded galaxy dissolves and the silence becomes unremarkable. More recent work has built on this foundation. In 2024, several papers explored what's called the multi-filter framework, which moves beyond the idea of a single great filter and considers the possibility that multiple independent filters operate at different stages of civilizational development. Rather than one catastrophic bottleneck, the origin of life, or the jump to multicellularity, or the development of technology. The multi-filter model suggests that each transition carries its own probability of failure, and the cumulative effect of many small filters can be just as devastating as one large one. Think of it like a series of locked doors between you and the exit. No single door is impossible to open, but if there are 50 doors and each one has only a 50% chance of yielding, the probability of making it through all 50 is astronomically small. A civilization doesn't need to face one impossible barrier. It just needs to face a long sequence of merely difficult ones. Another thread of recent research involves information theoretic limits on interstellar communication. A fascinating paper from early 2025 explored the idea that the energy cost of sending a detectable signal across interstellar distances might be much higher than previously assumed, especially if you want that signal to be distinguishable from natural background noise. The universe is electromagnetic chaos. Stars emit across the spectrum, pulsars blast out regular pulses, supernova flood entire regions with radiation. Cutting through that noise to send a recognizable artificial signal requires either enormous power or exquisitely precise targeting, both of which impose costs that even an advanced civilization might find prohibitive for routine broadcasting. This doesn't mean communication is impossible, but it suggests that the galaxy might be full of civilizations that can talk but choose not to waste the energy on speculative broadcasts aimed at no one in particular. They're not silent out of fear or policy. They're silent out of efficiency. Shouting into the void is expensive, and nobody shouts unless they know someone is listening. Scholars still argue about how to weigh these various new approaches against each other. The Bayesian dissolution of the paradox has its critics, who point out that the prior probabilities you feed into the model heavily influence the output, and that choosing different priors can produce dramatically different results. The multi-filter framework is elegant, but difficult to test empirically, since we can't observe the failure rates of alien civilizations at various stages of development. The information theoretic argument is physically grounded but assumes that alien civilizations think about energy economics the way we do, which may or may not be true. Each new paper sharpens the picture slightly but also reveals new ambiguities, like cleaning a window only to discover another pane of dirty glass behind it. A quirky detail from the recent literature involves a 2024 paper that modelled the Fermi Paradox using cellular automata, simple computational models where cells on a grid evolve according to local rules. The researchers simulated a galaxy-sized grid where civilizations arose at random intervals, expanded at various speeds, and either survived or collapsed according to probabilistic rules. They ran the simulation thousands of times and found that in a surprising number of runs, the galaxy appeared empty from the perspective of any individual civilization, even when dozens of civilizations existed simultaneously. The reason was timing. Civilizations would arise, expand briefly, and collapse before their expansion fronts reached anyone else. The galaxy was populated but disconnected, ships passing in the night, or more accurately, candles flickering in the dark, each burning out before its light reached the next candle. The mainstream historical lesson embedded in this research echoes something that archaeologists have long understood about human civilizations on Earth. Most don't last. The average lifespan of a human empire is roughly 250 years. If alien civilizations follow a similar pattern, rising, flourishing, and collapsing in cosmically brief windows, then the galaxy could host millions of civilizations over its history without any two ever overlapping in time and space. You let these new ideas settle over you like layers of a blanket, each one adding a little weight, a little warmth, a little texture to the picture. The paradox isn't solved. No single paper has driven a stake through its heart, but it's changing shape, becoming less of a binary mystery and more of a probability distribution, a landscape of likelihoods that shifts with every new observation and every new model. The question, where is everybody, is slowly being replaced by a more nuanced question. Given what we know and what we don't know, how surprised should we actually be? And the emerging answer, tentatively, cautiously, with all appropriate caveats and error bars, is maybe not very surprised at all, so here you are. 20 sections deep into the longest, strangest, most sprawling detective story the universe has ever posed, and the suspect list is pinned to the wall of your mind like a conspiracy board in a movie about a very tired but very thorough investigator. You've got the great filter lurking somewhere in the chain between dead chemistry and living civilization, catching species like a net catches fish. You've got the rare earth hypothesis, arguing that this planet and everything on it is such a preposterously unlikely accident that we might as well be a typo in the cosmic manuscript. You've got the zoo hypothesis, with its invisible fences and silent zookeepers watching you the way a naturalist watches a beetle, patiently, carefully, and with absolutely no intention of introducing themselves. You've got the dark forest, cold and game theoretic and ruthless, where every civilization hides because the alternative is annihilation. You've got Berserker probes, self-replicating machines sweeping the galaxy clean of anything that dares to broadcast its existence. You've got the simulation argument, dissolving the paradox by dissolving reality itself. You've got self-destruction, the bleakest and most human of all the explanations, suggesting that the distance between discovering fire and burning down your own house is shorter than anyone wants to admit. And then the stranger candidates, the Estivation hypothesis, with its sleeping giants waiting for the cosmic thermostat to drop, the Grabby aliens model, with its expanding bubbles and the implication that we might simply be early to a party that hasn't started yet. The detection problem, reminding you that searching for radio waves in a universe that might communicate via gravitational ripples or neutrino beams is like scanning for smoke signals in a world that invented the telephone. The intelligence trap, where dolphins and octopuses quietly demonstrate that being brilliant doesn't guarantee being technological. Panspermia, scattering seeds across the void without any guarantee that those seeds will grow into anything that asks questions. The UAP files, suggestive and frustrating in equal measure, offering blurry footage and sworn testimony, but not the kind of unambiguous, reproducible evidence that would make a physicist set down their coffee and say, well, that settles it. The Transcension hypothesis, where civilizations dive inward instead of outward, disappearing into the quantum foam like submarines descending below the thermocline. And the newest Bayesian and multi-filter models, arguing with quiet mathematical authority that the silence might not be a paradox at all, but simply the predictable consequence of multiplying a lot of uncertain numbers together and getting a distribution wide enough to include zero. So have we solved it? Have we finally found the answer to Fermi's lunchtime question? You already know what the honest answer is because you've been paying attention, and the honest answer is no, not definitively, not in a way that would satisfy Fermi himself, who liked his answers clean, quantitative and backed by data rather than speculation. But what we have done, what the last 75 years of thinking about this question have accomplished, is something arguably more valuable than a single clean answer. We've mapped the territory, we've identified the possible explanations, stress-tested them against what we know about physics and biology and the observable universe, and narrowed the field to a set of hypotheses that are at least internally consistent and at most genuinely profound. The paradox hasn't been solved, but it's been transformed from a single unanswerable question into a rich, structured landscape of possibilities, each one telling us something important about the nature of life, intelligence, technology, and the universe itself. And here's the thing that might matter most, the thing you can carry with you as the night deepens and your eyelids get heavier. Every single explanation for the Fermi Paradox, from the most optimistic to the most terrifying, tells you something remarkable about where you are right now. If the great filter is behind us, you're a survivor. If it's ahead of us, you're living in the most consequential period in your species' history, the window where choices matter more than they've ever mattered before. If the rare Earth hypothesis is correct, you're standing on the most extraordinary planet in the observable universe, a world so improbable it might as well be a miracle. If the dark forest is real, the silence of the sky is a warning, and caution is wisdom. If the aliens have transcended into inner space, there are dimensions of reality waiting to be discovered that we can't currently imagine. If we're in a simulation, someone thought your story was worth running, which is a strange kind of compliment. And if the Bayesian models are right, if the silence is just the expected outcome of honest uncertainty, then the universe is still an open book, still unwritten in the places that matter most, and the next chapter might contain anything. Scholars still argue, as they should, about which of these explanations is most likely. The debate will continue for decades, maybe centuries. New telescopes will be built, new data will arrive. The James Webb Space Telescope might find a biosignature that reshuffles every probability estimate we've ever made. A future SETI project might detect a signal that turns the Fermi Paradox from a philosophical puzzle into a historical footnote. Or the silence might persist, deepening with every new survey, every new null result, until the question itself becomes less urgent. Not because we've answered it, but because we've learned to sit with it, the way you sit with any profound uncertainty, patiently, humbly, and with your eyes open. You remember that crocodile dung sunscreen from... Wait, no, that was a different script. But you do remember the lunchtime question, the one Fermi asked over his tray in that New Mexico cafeteria in 1950, and you realise that the most remarkable thing about it isn't the question itself, but the fact that it's still alive. 75 years later, it's still the most important question nobody can answer, and it's still capable of making a person lie on a hillside at an unreasonable hour, staring at the sky, feeling simultaneously tiny and significant, alone and connected, frightened and comforted. That's the paradox behind the paradox. The question that reminds you how small you are is the same question that reminds you how extraordinary it is that you're here to ask it. And now the night is doing that thing where it gets very soft, very still, like the whole world has exhaled and forgotten to breathe in again. The stars are still there, every single one of them, burning their ancient light into a silence that might be empty or might be full of sleeping giants, hiding civilizations, expanding bubbles, and transcended minds. You don't know. Nobody knows. And for tonight, that's okay. The sky presses gently down, not with weight but with a kind of velvet patience, and you feel your breathing slow to match the rhythm of the dark. The grass beneath you is cool and forgiving, cradling the shape of you the way the universe cradles the shape of this one small planet, suspended in nothing, held together by forces so fundamental they don't need names. The questions are still there, all of them. The filters, the forests, the sleeping giants, the dolphins who never built radios, but they've softened now, their edges rounded by the hour, their urgency fading like the last glow of a sunset you watched so long ago it feels like someone else's memory. Let them fade. Let the paradox rest where it belongs, in the space between what you know and what you wonder, a space that's wide enough to hold everything and quiet enough to hold you. The stars aren't going anywhere. They'll be there tomorrow night and the night after, burning their slow, patient light into a darkness that asks nothing of you. Your eyelids are heavy now, and that's fine. That's exactly right. The universe has been waiting 13.8 billion years. It can wait a little longer while you sleep. So let the night fold around you. Let the questions dissolve into dreams, and know as you drift off that whatever the answer turns out to be, wherever everybody is or isn't, you were here on this one impossible night, on this one impossible world, asking the most beautiful question a mind can ask. That's enough. That's more than enough. Sweet dreams.